Hello.
Yes, sir. I can hear you.
Uh-huh. What is the time now?
It's 9:45. We are going to start at 10.
Oh. In the meantime, if any, she has not yet given any lecture so far.
Yes. Yeah.
But in the meantime, if any other student has something to ask me,
Yeah.
because they have attended a lot of my lectures, they are quite welcome.
Sure. I'll type it in the chat and they can revert back if they have any.
And you can
problems.
unmute them also if they have they are asking a question.
Yeah, sure, sir.
Okay. So if anybody has a question, in the meantime, I will answer. I will not take away time from the meeting
Yeah, yes, sir.
for her lecture. So Rajakatha Chand was asking me, Bhupatha Chand was asking me a lot of questions. Do you have any question now? Do you have any comment on the lecture, how I can improve?
No, sir, not yet. Not yet, sir.
I mean, is it going all right? I mean, am I very, is it looking very technical or fast or, this is one of the very hard theorem. Yeah.
Sir, I'll study. I'm not able to catch up with the pace right now because I mean studying is a problem. I mean the time. I'm getting much too less time to study. So once I'm able to study well, I'll surely let you know.
And
Okay.
do you have my book also with you, or can you get hold of?
Yes, sir. Yeah, yeah.
So that
Yes,
will be
sir.
helpful
Yes.
because I have I'm omitting few lines, few proofs. That will be helpful.
Okay.
Ujjwal was also
Okay, sir.
asking me questions from time to time. Dhruva asked good questions. So if there are any questions before Madam starts, I can answer. It is a slightly in the beginning, it may look a bit technical, but keep patience. Most it actually requires patience, not too much of I will say mathematical maturity. Not too much. Too much of mathematical background, I mean. Maturity, yes. And Manoj Babu. Are you being seen? Are you comfortable sitting like this? Hi, Kashyap. You unmute yourself.
Yeah. How are you doing, sir?
I'm doing fine. I have an offer to make you.
Yes, sir. Yes, sir.
You buy one, get two. Huh?
Yeah. Yes, sir. Noted, sir. Noted. Noted.
Noted, huh?
Yeah.
Huh?
For lectures and so on. Oh,
No.
for teaching.
They are looking to appoint logicians.
Yes. Right. That's a good one.
So I said, I am ready. I will try. Okay. And then I said, now I am giving an offer. Buy one, get two. Get one. No, buy one, get one free.
Yeah. Sir. How are you doing, sir? How is it? How is it going so far?
You tell us.
No,
I'm
sir.
enjoying.
What am I, sir? I think the students should say, the participants.
Yeah, that is what a student should say.
Yeah. It's for them.
But I am actually quite happy with
Yes,
the.
sir. Because why I'm asking is this is the first time we are probably doing it virtually. So that's why I'm probably asking you.
No, are you talking of the technical thing, or are you talking of
No, this experience for you,
technology,
this-
or are you talking of the?
No, sir. I'm talking about the mode in which we are organizing this conference. It's
Oh,
not
technology.
physical this time. It's virtual. Are you comfortable?
So for technology, I'm wrong person to ask, but I can tell you one thing: I had no difficulty so far.
Okay, sir. Okay, that's what I
Either to
wanted to know.
listening or to. I have been listening all the lectures. I had kept my camera down and muted, but I was listening to all the lectures so far.
Sure, sir. Sure.
And
No, sir, because some people believe that doing it virtually sometimes feels like a compromise because
see,
of the situation.
those who have heard me lecturing on the board,
Yes, sir.
they may be mixing a lot
Yes,
over
sir.
this
Yes, sir.
thing.
I'm sure.
Because I sing and jump and dance over the board. Sujata will ask you.
I heard, sir. We are surely missing the energy, your energy.
What are the things you have heard about me?
Yeah, that you are very energetic while writing on the board.
So, but by sitting, I cannot
Yes,
sing
sir. We
and
cannot jump around.
dance. Also, I don't like lecturing from notes.
Yes, sir.
No, what he is saying is, but I agree that it is a compromise. He is saying that virtual is a compromise.
Virtual is
It
a
is a
compromise.
compromise.
That is
It can't be helped. That's a different thing.
Yes,
It is
sir.
a compromise.
Yeah.
the time now. What is the time?
We have
Time-
about 6 minutes.
9 minutes
It's still there is time.
Right,
Now,
right.
another thing is that there is a compromise because when I am lecturing on the board or when a teacher is lecturing on the board, students see things coming out,
Yeah.
in a natural. Whereas if it is written on the notes, that teacher's mind is not working that much, it's not manufacturing the things.
Right.
So I don't like, I never take notes to my class.
Yes, sir. Because it sometimes kills spontaneity.
Pardon?
Spontaneity.
It kills the
Spontaneity and this.
Yeah.
So there is that problem with this. On the other hand, I don't think people from so many places would have joined the thing.
Yes, sir.
And now things are available. Now world has become one.
Yes, sir.
So we can listen to lectures from people all around the world, and people from all around the world can listen to us.
Definitely, sir. And also one other thing that this whole virtual organization has helped many of us is that funding is always a difficulty while you organize conferences. You apply for funding with NBHM, all these big organizations, and they're never, prompt in ensuring that the funding reaches us.
But
Sometimes it reaches after the conference, sometimes before.
Another good thing that you people have done is that you have put your video recording and you have put it on YouTube.
Yes, sir.
So I have told many people to join on YouTube, not to disturb the classes. So my students and various other places are on YouTube, I know.
Right.
And they can join. Some of them mix at the time of the lecture because they have some other work, they have some other class.
Right.
But later on, they can
Yeah,
they
definitely,
can,
sir. That is the idea. That is the idea.
that is a very good thing.
Yeah, yeah, yeah.
And talking of funding, so I agree that organizers have, for organizers, it has become much easier, but it is a loss for the teachers, the speakers.
Yeah.
I can.
I knew you would say that.
Huh?
I kind of anticipated you might say that.
Sorry?
No, I said I kind of anticipated you might say that.
By now you know what I am. Huh?
Yeah. Yes, sir.
At least I could have gone and seen Sanchi Stupa, and you know, you people have taken me around, shown Bhopal, and
Yeah.
Well,
taken me
actually,
to,
one does miss that a bit.
and one misses that, and then go to a taken me to a restaurant and treated me fantastically.
Yes,
Ah,
sir. Yes, sir. That
and all
experience,
those
yes, yes.
things. So they are missing.
Physically
So
organizing
it's all
it.
right. It's all right, because I have already enjoyed a lot that hospitality and monetary benefit a lot. So
Yeah. So
now I
maybe
don't need
sometime
it.
in the near future, I'm sure Sujata and the ALI would consider physically
No,
organizing it.
I'm not making any application. Sorry.
Consider what?
No, Sujata. I'm not making any application.
Consider what?
Paying to the teachers.
Yeah.
No, Sujata. I'm not making any sense.
That is surely not done.
What?
Paying to the teachers for this, that is never done.
No, not done. But how about free food? Free seeing places. But like seeing
The
place
whole
is a big thing.
experience
So
is
for that
really,
matter, personal interaction is also a big thing which one misses.
No, we are doing interacting. I don't think. I don't think I would have interacted with Kashyap if I had been lecturing in Bhopal, because it is not his subject, you know.
Oh, he's coordinating.
So only those who are
the volunteers.
No, those who are in the conference, with them we meet a lot.
Yes.
Yeah. Sir, I think that's where you are mistaken, sir. I visit and talk to everybody who visits our department, regardless of what subject they are in.
No, but in this series of lectures, how can you do when you have other work right there?
No, there is always time in between, sir, to catch up with guests.
Okay.
It depends on the
But
person.
generally, this is what happens. I mean, I'm talking.
Yeah. Sure, sir. Sure.
Let us keep eye on the
time. Somebody must be doing it.
Yeah, we have 2 minutes left.
Yeah. So now we stop.
Yeah, we can probably wait for a minute.
Yeah.
Connected to cloud server, whatever that is.
It's probably time, right? Sujata, shall we get started?
Yes, please.
All right. Good morning, participants, and good morning, everyone. I welcome you all to the morning session of the third day of ISLA 2020. And this morning, Professor Sarbadikari will be beginning a lecture series in the conference. And Professor Sarbadikari doesn't need an introduction, but she retired from the Indian Statistical Institute, Kolkata, and areas of specialization include descriptive set theory and model theory. So, Professor Sarbadikari, I would request you to, begin your lecture this morning.
Thank you.
So, when you say, I will put this.
But shouldn't you put it right now?
Right now?
Okay, I don't know. Well,
Yeah,
thank
can
you.
probably
And
share
I
your
suppose,
screen, sir.
yes,
Yeah,
we should begin perhaps.
yeah, you can share your screen, madam.
Wait, wait, minimize.
Right? I see.
Shall I make it full screen or?
Or is this better? I don't know.
No,
Maybe
full
this is
screen is better.
You can probably
Ah.
make it full screen, sir.
okay.
Yeah.
Okay, then.
So you want to say anything or should I make it full?
You can make it full screen. It's like this. Okay.
Looks good, sir. Looks good.
Acha, is she being seen or?
Yeah, sir. It is visible, the screen.
No, is she visible or not?
Yes, sir. She's also. She's also.
Okay.
Oh, am I?
Of course.
Okay, then.
Yeah. No.
Okay, then we should begin. And what I'm talking of is cardinal arithmetic. So what are cardinal numbers? Well, they are sort of, in a way, you are extending the natural numbers and you will do arithmetic. The idea is we think of cardinal numbers, cardinality of sets we usually think of as the size of sets. Well, B.V. Rao will be doing some more on it. And he will introduce some sets as cardinal numbers. So we'll come to that. So at the moment, let us think of, well, we are talking of cardinal numbers as size of sets, but what are size of sets? How do you talk of size of a set? Okay, we know finite sets, but infinite sets, well, okay, how do you kind of decide on their size? Which are the same size? Are they all the same? Are some, or can you compare such things? So we say that two sets are equal in size. They have the same cardinality or the same cardinal number if there's a one-to-one match between them. The same number of elements we think of. So that means there is a bijection between them. And then we write like this, mod x equal to mod y, if they have the bijection between them. Now, what B.V. Rao will do, he hasn't done this yet, probably he will do this, is for each size, he will kind of pick one special set as a cardinal number. He started doing that. He said, okay, he called something n and something. Okay, I'll come to that. So he said he will pick some special sets as cardinal numbers, and they will have this property that for each set, to each set x, we can associate one particular cardinal number, which we call mod x. That's also a set, a special set, with the property that these two have the same size, they have the same cardinality. There's a bijection between them. And it is kind of unique. That is, if two sets have the same size, same cardinality, then mod x and mod y are the same. And
hello, ma'am.
yes.
Ma'am, I'm facing some trouble with the first condition. X
Yes.
and mod x have the same cardinality.
Yes.
So isn't mod x a number?
No. It is a set. Yeah, okay, it is like this. Remember, B.V. Rao did this. he called the empty set 0. Then he called the set containing the empty set 1. So these numbers are really sets. Then he called the set containing 0, 1, 2. So when I talk of a number n, I mean the set with n elements, 0, 1, 2, up to n minus 1. Is that all right?
Okay. Yes, yes, thanks.
So that I was about to actually say that for example, I was about to say that, for example, any set with n elements, to it I assign the cardinal number n, which really means the set 0, 1 up to n minus 1. And we call it n. So that's the example. That's the finite set. And generally, cardinal numbers are denoted by these Greek letters, lambda, mu, nu, etc., with or without suffix. Okay, now we have to also compare them. Which sets are larger than which are bigger, which are smaller.
Hello, ma'am.
Yes.
Ma'am, so in the first point that x and mod x have the same cardinality, you mean that mod x is a set?
Huh? Yes, mod x is a set, yes.
Ma'am, but in the second statement, it is written that if sets x and y have the same cardinality, then mod x is same as mod y.
Yes.
If mod x is a set, then how we say that mod x is same as mod y?
It's the same set. You see, take any set with n elements, for example. Okay. It can be A1, A2, An, B1, B2, Bn. These are different sets. But for all of them, the cardinality is n, which is the set 0, 1 up to n minus 1. Okay?
Sir, ma'am, if the set has infinite infinite cardinality, then what
yes. If the set has infinite cardinality, when will they be the same? Is that what you're asking?
Ma'am, like let us suppose we have two sets x and y, and they have the cardinality means aleph naught. So
right.
How we denote this mod x is same as mod
x?
Well,
mod x is aleph naught is really the set of natural numbers, 0, 1 up to. It is a set. Okay. Vivi will probably do that. Vivira will probably do that. Yes, aleph naught is actually the set. Just as n is the set 0, 1 up to n minus 1, aleph naught is the set of all natural numbers, 0, 1, 2, etc.
Okay.
All right?
Yeah, okay.
Okay. So now we start comparing sizes of cardinal numbers. When is one less than another? And you tend to think, okay, a proper subset should be smaller, right? But okay, it is not really the case. Always, for example, look at the natural numbers. What is that? 0, 1, 2, etc. And then I take away 0. But they are the same size, no? Because n going to n plus 1 is a bijection from 0, 1 up to all natural numbers to all natural numbers except 0. Okay. So that is not true, really, that a proper subset is necessarily smaller. So we do like this. We say that mod x is less than equal to mod y if mod x is the same cardinality as a subset of mod y.
Hello, ma'am.
Well, x, yes?
Ma'am, can you change the slide?
Can I change the slide? Oh, I see. Okay. We say that mod x is less than or equal to mod y, and we write like this. If there's a subset of mod y such that it is equal to mod x. I mean, its cardinality is equal to the cardinality of x. And that is the same as saying, see, we take for specific thing, we take that a subset of mod x should be like a subset of mod y. But we could as well say that a subset of x has the same cardinality as a subset of y. Or there's a bijection from the subset of x. X has the same cardinality as a subset of y. Or there's a bijection from x onto a subset of y. We can say that. It means it's the same thing, right? And in this case, we say mod x is less than equal to mod 1, or cardinality of x is less than equal to cardinality 1. And when is it less than? When cardinality of x is less than equal to cardinality of y, but cardinality of x is not equal to cardinality of y. In other words, there's a, okay, x can be empty, or there's a 1-to-1 map from x to y, but there's no 1-to-1 map from x onto y. Okay. Now, okay, there's nothing to say. These are notations. All natural numbers we denote by n and r. What is a countable set? Okay, first of all, what is a finite set? It is of cardinality n for some n. That we have already explained. What is n? It is this set, 0, 1 up to n minus 1. And then we call it finite. And if it is either finite or has the same cardinality as natural numbers, we call it countable. And this is Aleph 0 is, okay, it is the cardinality of natural numbers. It's denoted by Aleph 0. As I already explained, it's actually the set of all natural numbers. And if a set is not countable, it is called uncountable. Okay. Okay, this I have already said that they can be treated like natural numbers. And okay, this you can already see that it's all about 1-to-1 maps. So we need a lot of results about 1-to-1 maps. And now this is the question I was about to ask, this first thing, that after all, are all infinite sets countable? Are they all equal, or are there some uncountable? And this is the first example, that take all sequences of zeros and ones. It is not countable. Means what? Means it is, of course, not finite, that is clear. And there's no bijection from the set of natural numbers to this set of sequences of zeros and ones.
Hello, ma'am.
Yes?
What do you mean by a set of all sequences of zeros and ones?
You understand a sequence of real numbers?
Yes.
So, if I call it a sequence of zeros and ones, if all the entries are, look at a sequence x1, x2, x3, etc. If all the xi's are either 0 or 1, I call it a sequence of zeros and ones. So, there are many such, right? 1 0 0 0, 0 1 0 0, 0 1 0 0, 0 1 0 1, 1 1 1. All these are sequences of zeros and ones. You understand?
Yes, yes, yes.
There are no other entry except 0. Okay. So, and we say that you cannot get a 1-to-1 map from the natural numbers onto this set of sequences of zeros and ones. Okay. So, if there is, we'll get a contradiction. So, suppose there's such a map F. All right. So, and Fn is, I've written, suppose Fn is this sequence, xn0, xn1, xn2, each xni being 0 or 1. So, I now give you a sequence of zeros and ones, which cannot be an n, which cannot be Fn for any n. How? By changing the nth entry. For example, I take y0 to be 1 minus x00, y1 to be 1 minus x11, like that, yk to be 1 minus xk. Then, what is the sequence y0, y1, y2, etc.? We call it y bar. It is still a sequence of zeros and ones, but it is not Fn for any n, because we have changed the nth coordinate each time. So, that means you cannot get a 1-to-1 map from the set of natural numbers to this set, the sequences of zeros. So, this set is uncountable. Okay. Now, okay. Now.
Hello, ma'am.
Yes.
I mean, I couldn't understand how x is infinite in this case.
How? What did you say?
the set x
Huh?
x of all sequences of zeros and
How
ones.
is it infinite? Is that what-
Yes, you. Yeah.
Oh, how is it infinite? Oh, yes, 1, 0, 0. You know, 1 in the nth place.
Yes, ma'am.
That
Yeah.
is the nth sequence, say. Then aren't we getting infinitely many? 1 in the first
Right.
place.
Right.
So there are infinitely many.
Yeah. Okay. Thank you.
All right. Now we will look at, see, countable sets are something a bit special. So we'll first look at properties of countable sets. Sets of cardinality Aleph 0. So, and for that, we have to concentrate on n really, on natural numbers, right? Because all the countable sets are, well, like a subset of natural numbers. So, or actually, what I should say is, I have said every infinite subset for some reason. What I should say is every subset of n is countable. The reason I have just written this is probably the following. Finite sets are anyway countable. We have accepted it. But if I take an infinite subset of n, it is still countable. Infinite subset of natural numbers. Well, that's easy enough. This proof you can all see. You just write them in increasing order. A0 is the smallest one. A1 is the next one. A2 is the next one. So like that, you will get a one-to-one match. I mean, I to AI will be a bijection from your set N to your set A. So every infinite subset of this is counted. And this you can check for yourself from this. It follows that if you can see, you can always see that you can write down a countable set as a sequence. If it's a finite set, you repeat the limits, otherwise you don't have to. But suppose you take a sequence, it may or may not have repeated elements. Okay, then its range is countable. That you can easily see now, right? It matches with some subset of natural numbers. Okay, now now we look at some other sets which are countable, which this is interesting because it should be larger. No? This n cross 0, 1 to, and n, or n cross n and n, yeah? All of the same cardinality. And I have written down the matching. Mn going to 2m plus n. That is a bijection from n cross 0, 1 to n. And this mn going to 2 to the power m2n plus 1. Sorry, this should be 2n plus 1 minus 1. Huh? Otherwise, we miss the 0. Somehow the correction didn't. So,
okay, we will make it. You
it
just
will be-
point out. So, see, you do the cursor. You know, if you move the cursor, they can see.
What can they see?
Where your cursor
Oh,
is.
okay.
You take your cursor.
Okay. Here, there should be a minus 1 here. It should be 2 to the power m, 2n plus 1, minus 1.
Otherwise, you want you
Because otherwise, 0 doesn't come in the range. And that is a bijection from n cross n. So this shows what? This says that, okay, this is easy, that they are all of cardinality Aleph 0, n cross 0, 1, n cross n. So, which means that take any countable set, x cross 0, 1, and x cross x are countable. As I say, if it's finite, nothing to say. If it is infinite, then it is like n. And from this, it follows that if you take a sequence of countable sets A0, A1, A2, and then take the union, that is also countable. Why? This is the proof that you write, okay, AN is a countable set. You can write it as a sequence, AN0, AN1, AN2, like that. And then I write, so what is the union of ANs? All the ANMs, N and M ranging through natural numbers. Now, if let psi NM is decay, we have already seen psi, the bijection from n cross n to n. So you put bk to be ANM, where k is psi. So now we have written this union down as a sequence. And so it is countable. All right. So now with countable sets, being something special we have done. Now we just come to general sense, any sense. No.
Hello, ma'am.
Yes.
Ma'am, in one book I've read that for proving that countable union of countable sets is countable, you have to use the axiom of choice. But
Yes, that's right. That is right.
But in this proof, I don't see the axiom of choice.
Oh, because you have chosen the way you have written the ANs. You've chosen this sequence. For each n, you have chosen this enumeration.
Oh, okay. Thank you.
He brought it up. Okay, now there's nothing to say,
Which
right?
axiom do we need? I didn't follow.
What's that?
Which axiom do we need?
Axiom of choice.
Oh,
Where do we need, he was asking.
okay.
Where have I used the axiom of choice? Because for each n, I have chosen an enumeration, a particular way of writing an.
But
So,
that we can do by using just the definition of countability, right?
but there are many ways of writing, you see. It is countable, there's a match, but that match is not unique.
But then the axiom of choice just says that when we have a collection, then there is a choice function. Here,
Right.
What type of choice function are we using?
It is like this. See, for each an, we have a collection of, the way you write an, collection of the enumerations.
Okay.
And now for each of them, we are picking one. That is the choice. For each n.
Also, choice function among the enumerations of.
Right.
Okay.
Right.
Yes. Thank you.
Okay. So now we come to general sets. We are no longer confining ourselves to countable sets. And this is sort of easy to see that this less than equal to relation is transitive. X less than equal to y less than equal to z means what? There's a one-to-one map from x into y. Okay, or x is empty. All right. And then there's a one-to-one map from y into z. So you combine the two and you get a one-to-one map from x into z. And okay, now you may wonder why I'm saying all this. That less than means what? That mod x less than equal to mod y, and they are not equal. Now, this is also transitive. Why am I saying it? Because, see, suppose mod x less than equal to mod y and mod y. Okay, suppose mod x less than mod y and mod y less than mod z. See, I am saying mod for convenience. I mean cardinality, of course. Then, using this, we can say mod x less than equal to mod z. But who says that it cannot be equal now? Now, how it cannot be equal, how do you know? So that needs a proof. And for that, we need this theorem, Cantor, Schroeder, Bernstein, Dedekind theorem. Well, it's called Schroeder-Bernstein theorem usually, but then Cantor and Dedekind had a lot to do with it. So, hence all the phonemes. Yeah, yes, because Cantor conjectured it, Dedekind also gave a proof to him. So, and that's why, and that theorem says this. Yeah, it says that this relation is like this: mod x less than antisymmetric. Mod x less than equal to y and mod y less than equal to x means mod x equal. Implies mod x equal to y, and that does need a proof here. So let us see.
Ma'am, I have a question.
Yes.
When you say mod x equal to mod y,
yes.
The two sets are equal, which means, what do you mean by that? You mean that the mod x is a subset of mod y and mod y is a subset of mod x, right?
No, I don't. Yes, okay. I mean that if it is mod, yes.
Right. But then what is this theorem saying? Is this
theorem, I see. No. Sorry. Mod x less than equal to mod y does not say anything about mod x being a subset of mod y. Yeah.
But your definition is less than or equal to, is that right? No? because mod X itself is a set and mod Y itself is a set. And so when you
then what I said really was that mod X is bijective, there's a bijection from mod X to a subset of mod Y.
Oh, okay.
I didn't say it was
That is
equal.
what you mean by mod X less than or equal to Y. Okay.
Injection from X into Y.
It's as same as there's an injection from X into Y.
Okay.
Right?
Thank you.
I didn't actually say it is a subset.
Okay.
Okay, it will, since this is there, it will turn out to be so, but
sure, okay.
I didn't say it.
Yeah, thank you.
Ma'am, so
yes,
you said
yes.
cardinality of X, this mod X is less than, I mean, I was confused with this, that mod X we denote something like, let's say 0 up to some n minus 1.
Yes, okay, but let us not do that because it may be not, it may not be finite or countable, it may be something much larger. So
Right.
let us forget what it is exactly. Yeah?
Okay.
It is some set, but that let us forget that and let us look at X and Y.
Right.
This is same as saying that from X you can get an injection into Y. Forget the mod part of it. Because you see there's a one-to-one match. Mod X is some special set. But there's a one-to-one match from X and mod X, X to mod X, right? There's a bijection.
Yes,
okay. And there's a one-to-one match from Y and mod Y. So X is like a subset of Y and mod X is like a subset of mod Y is saying the same thing, right? You think of it as though you are simply changing the label. X to mod X, you are simply changing the label by the bijection. Or if this confuses you, are you finding this confusing? Hello?
No, ma'am, it's okay.
You think of X and Y actually. This is said. So, because that's precisely what mod X less than mod Y is saying, that there's a one-to-one map from X to Y. And then there's a one-to-one map from Y to X, because mod Y less than equal to mod X. I did say when I defined, right, that that's equivalent, whether you take the mods or whether you take the map from X to Y, it is the same. Okay, now what we have to do is define a bijection from X onto Y using these. And there is a bit of a manipulation here. So here is what you do. Take for any subset, to any subset A of X, we associate another subset of X, HA, by, okay, you look at that. HA is, you take first F of A, you go into Y, take its complement, then take G, come back to X, and take its complement again. That is H of A. And suppose you can show that some H, there's some E such that HE is E. Then what will you have? X minus E will be G of Y minus FE, right? Or all these GFs are all one-to-one. So your G inverse of X minus E will be Y minus FE. And now you can define H on X by, it is F on E and G inverse on X minus E. That will be a bijection from X to Y. Okay. So we have to find this E though. I've so far only said that there is a E. So for that, look at this. If A is subset of E, B, then HA is subset of HP. You can do it by, computing. If A is subset of B, if A is subset of FB, then the inclusion is reversed when you take complement. Then like that, if you do, you will find that this is what you are getting. You write it down. And then this is, of course, again, by writing it down, you will see that H of a union is union of the H's for any A. Okay. So now,
I didn't quite get that. What is H of A? Can you explain it?
What is H of A? Okay, you start with A and pick its image F.
Hello, ma'am.
Yes.
I think it would be better if you're able to explain this with a figure, with a figure, like two sets and how the map actually goes, like the subset being mapped to another subset.
Wait just a minute.
My book.
Just a minute. I have to find one such. Okay, let's see. Suppose we start with the empty set. I don't know. I don't know. That's somewhere in the room, bedroom. Achha, so let's see. Let's start with the empty set and see what happens. Suppose A is empty. Okay, so FA is empty. So, what did you want illustrated? Just a minute, I missed that. What did you want me to illustrate? Hello?
Ma'am, like usually you can actually make an illustration out of this, right? That is, you just draw a subset, like you draw two
But how do I
circles.
draw? That's the trouble. Yes, I would love to do that, but how do I draw?
Yeah,
I can only give you subsets, right? I have no way of drawing a picture here. You can draw the picture for them?
No, not picture.
Oh, you'll show them. Just a minute, just a minute. You will be shown a picture. They want to see a picture.
Okay. I'm showing you the picture from my book. Now let me see. This is the book. Can you see?
Yes, sir.
This is the book. Can you see a course on Borel sets?
Yes, sir.
Okay. So
No, sir. The graduate text in mathematics. That's all we can see. Yeah.
now.
Yeah.
But that doesn't matter. They
Okay.
should see the picture.
No. So now from this book, so this is a reference. That is why I am telling you. Okay. Now I am showing you the picture. Now here is the picture. Can you see?
Sir, can you just move the book a bit up? Just a bit up. Right.
Okay. Now, let me see. Can you see the picture?
Yes, sir. Just a bit up.
Yes.
Yes.
Now you
yes.
see the ellipse on the left hand side is the set X. Yes.
So can you move it a little up, sir?
Yes, sir. Yes, sir. Over there. Yeah.
Okay, and the ellipse on the right hand side denotes the set Y.
Yes,
okay?
sir. It is very clear. Very clear.
Now take a subset A of X.
That's also drawn.
Here. Subset A of X. Here. And then take its image.
Shall I do that? Here is the image FA.
FA.
Here is Y minus FA.
And then take its image.
G brings it here.
And then take the complement. That is what you are looking for.
Okay. And the complement will turn out to be this.
Can you see?
Sir, so the complement will turn out to be A, right?
Yes.
That is what you are looking for. And that is what she had called E.
Okay.
Okay. Before I give her the chair, let me tell you one thing. These 4 names, Cantor, Schroeder, Bernstein, Dedekind, is given by me. Reason is Cantor was the one who conjectured, who was trying. Dedekind was the first who communicated the proof to Cantor, and that is the proof that is being presented. But that letter was lost. So people didn't know the proof of it, and independently, Bernstein and Schroeder also proved, but later on, Dedekind's proof surfaced. Among the latest communications between Dedekind and Cantor.
Okay, sir.
So now that is how it is defined. You first take image under F, then take its complement in Y, then take its image of that complement under G, and then take the complement back. And she's looking for a fixed point of that. Okay?
Sir, then my question would be, why do we define H of A then? Like, we could have just worked with A. Why do we define?
No. That is a notation. That is only notation. Huh?
Okay.
Okay. Now, one thing is there. Have I publicized my book to all of you? And are you going to buy my book, all of you?
Definitely. Definitely.
Yeah, sorry, I cannot draw, you see, so we had to go through this process. Is it all right now?
Yes, ma'am, got it.
Sure, ma'am.
Yeah, sorry, since I can't draw, we had to do this complicated process. Okay. So, how far are we? Oh, I did this. Okay, so we are going to find this E wicked work. And you start with the empty set and you go on applying H. And take E to be the union of all these ANs. Now it is clear, of course, that HE is E, right? Using the properties. Because HE would be union of HAN. And that would simply be the union of ANs again. Okay. So that is now the thing is, I did say that we want to see that these behave like our usual natural numbers. So this less than equal to has satisfied antisymmetric. Now,
if I may ask a question, I mean, the crux of this proof is defining H. Am I right?
Yes, yes,
Am I right?
yes.
Okay, so right. Thank you.
That is there is a long and involved proof, like he was saying, which came later, but this is a very neat proof.
I'm not saying long.
No, the proof about which you are talking. That is not so neat as this one somehow. It is very neat. No, it's not very long and involved, no, but it's not as neat as this. This is a neat proof with this H. Yes, the crux is the H.
Hello, ma'am.
Yes.
Ma'am, this proof uses the Tarski's fixed point theorem, right?
Is it?
Well. See, you can write it down as a fixed point theorem, general fixed point theorem.
Yeah.
And maybe it is called Tarski.
Yeah, I don't know. Maybe it is called that.
It is called some fixed point.
It is a fixed point theorem.
Okay.
No, but you are missing the point. Why H union? Because intersection of two sets is the intersection median. That uses
that uses 1 to 1.
So you go back and this part here.
Yeah. Oh, yeah. This part, I did miss out on these details. That why is H union AN is union of HAN? Because there, when you work out, you will see that you are using that intersection of two sets. The image of the intersection is the intersection of the image. That is not generally true. It is because it is 1 to 1.
It is 1 to 1 is
all the maps G.
No, G is 1 to 1.
G is 1 to 1.
So
Yes.
Just a second. Suppose this A is union. Suppose this A is union and AN. Okay. Then what will this be? Here you will get F of union and AN. But image union of the
Okay. I know what you are saying now. Okay. I know what.
So down.
I know what is the problem now. All right. It is this. That see, you take union in AN. F of union and AN, of course, will be union and FAN. That is okay. And Y minus that would now become intersection of these complements. Now when I take G, it will still be intersection of the G's because of G being 1 to 1. That is the point that since I didn't do the proof, I missed out. This is where you use 1 to 1. Is that okay, everybody?
Ma'am, could you repeat that?
Y is H of union and AN, union and HAN. Yeah, I had skipped the proofs, which is not a very good idea. So the thing is that you take union and AN. What is H of that? It is X minus G into here, Y minus FA, union and AN. Now, F of union and AN would be union and FAN. There's no problem there. Now, what is Y minus that? That is intersection over N, Y minus FAN. Okay. Now, take G of that. Now, G of that is intersection over n. Just a minute. What was it? It was intersection over n.
Y minus FA.
Yeah, I think I better, because I am myself getting up. Sorry, I better look at it myself. Yes. Just a minute, please. Unless I write it down to myself, I am getting all these confused. Yeah. So what I am having is G of intersection n, y minus FAN. And that will be intersection of n, G, y minus FAN, because G is 1 to 1. Otherwise, this would not have worked. This is where 1-to-1ness comes. And then when I take x minus this, again it will become union over n, x minus G, y minus FAN. And that will be union over n, HA. Is that all right now?
Okay, ma'am, I'll think about it.
I think what you have to do is, suppose you write it down. I also got confused, then I wrote it down and looked at it. If you write down the steps, do you understand what you have to write down at least? You have to write down A as union and FA, union and AN, do the F, do the complement, then do the G, and remember that G is 1-to-1, so that G of an intersection is the intersection of the G's. That wouldn't work unless G is 1-to-1. And then the whole thing comes out.
Okay, ma'am. Yeah.
Okay?
Yeah.
Okay. Yeah, I should have kept written that down here. Probably.
Hello, ma'am.
Yes?
Where is the 1-1ness of F used?
That is not used.
No, that should be used, right? Because you have that.
No, it is true without.
Well, no, it is not needed. It works without that. It's
Okay.
not used. You can see it's not used. This works without that.
No, ma'am, but we are like, from the fact that there is a map from A to B that is injective, and there is a map from B to A that is injective.
Oh,
Only
well,
then.
Oh, wait. At the last stage, when you define the map to be injective, there you will need it. See, at the end, we'll define a 1-to-1 map from A to B, right?
Ma'am, you mean small h?
I mean small h.
Okay.
Or whatever I have called it. Did I call it small h? Yeah, I called it small h, I think. Yeah, the last map, that uses 1-1ness, right?
Yes,
Shall I go back to it? Let's see. Yeah, I mean small h. This uses 1-1ness.
Ma'am, while defining capital H, don't we need F to be 1-1?
Well,
like,
defining capital H, no.
Okay.
But
And
then
when
finally
we are
you need it.
And when we are talking about capital H of E is equals to E for some subset E of H, there
we are not needing it, but we are needing it after that, when we are defining this map H.
Okay, thank you, ma'am.
Okay. All right now? All right. If it's all right, if this is all right, we go to the next thing, that we can compare any two cardinals. And this is called the law of trichotomy. And, well, we are going to, since B.V. Rao has already explained what is Zorn's lemma, and that is same as axiom of choice, equivalent, I will not go through this explanation, right? I will simply say that I am using Zorn's lemma to prove it. So, if one of them is empty, nothing to say, right? Of course, the empty set, is, less than equal to every other set. Cardinality of the empty set is less than equal to cardinality of every other set. So, now, suppose they are non-empty. And we look at, what do we want to say? They can be compared, x and y. Either cardinality of x and cardinality of y are the same, or cardinality of one of them is less than equal to that of the other. So for that, as I said, we'll use Zorn's lemma. So look at this. Look at the set of all AF, where A is a subset of X and F is an injection from A to Y. And partially order it by...
Hello, ma'am.
Yes?
In defining P, also are we using axiom of choice?
In defining P, we are using axiom of choice. Are we? Where?
Because you're choosing a function, a bijection, right? Bijection from A to Y.
Yes, we are choosing, but there's only one OIC. Are we doing it?
Which one?
This
No,
choosing
no,
an
no, no.
injection.
No, we are looking at all such.
We are looking at all such. That's right. We are not choosing we are not choosing an injection. We are looking at all such. We are
We're
looking
looking
at
at
all
all
AF.
injections.
Huh?
No, are
There
we
may be
looking
many.
at...
There may be many. Doesn't matter. We are looking at
No,
all of them.
no, ma'am. I'm asking for a given subset of X, you're choosing a particular injection, right?
No. We are looking at all possible A's and all possible injections from them. We are not choosing a particular one.
No, but when you define an ordered pair, are you defining it to be A, comma, some injection, right?
No. A comma any injection. See, suppose there are 10 injections from, just a minute. Suppose there are 10 injections from A to Y. F1, F2, F10. Then we have here AF1, AF2, AF10. All of them are in P.
Okay.
Okay, now? There's no choice. They're taking
So,
all of them.
ma'am, so you're taking all subsets, and for a given subset, you're taking all injections. So
Right.
all of, okay.
All possible. And then we are, that's why this partial order. Then we are partially ordering it by, well, what you would expect. F comes before BG if A is a subset of B and G extends F. And you can very easily see that this is a partial order. And if you take a chain, then you take union of all these AIs and you take all the put all the FIs together and get AF, and that gives an upper bound of the chain. So that by Zorn's lemma, there is a maximal element here. And we call it AF. Okay, now A can be, this is my claim that either A is the all of X or image of F, or I should have said F A equal to Y. I should have said F A equal to Y. This is a typo, I think.
Yeah, that is it.
I should have said F A equal to Y. So that either the domain of F is X or the range of F is Y. It's like that. And if the range of F is Y, then of course, this inverse of F will be a one-to-one map from Y into X, an injection. So in the first case, we'll have X less than equal to Y, mod X less than equal to mod Y. In the second case, we'll have mod Y less than equal to mod X. So yeah, but why is this claim true? Because suppose A is not X and F of A is not Y, then some point X0 and is left out here, some point Y0 is left out there. So I extend F by taking X0 to Y0. And this will sort of violate the maximality of AF. Okay. So we have shown this. So now the law of trichotomy follows. Because if both of these hold, then they are equal. So if mod X less than Y, then you cannot have mod Y less than equal to mod X. So exactly one of the three will hold, mod X less than Y, or mod X equal to Y, or mod Y less than mod X, where I can say mod X is greater than mod Y. Okay. Now, next thing is that if X is infinite, or other words, Aleph naught is the smallest infinite cardinal. X is infinite, and Aleph naught less than equal to F. And you will see here, you can see the use of choice very easily. I pick first A0 in X. Then, since X is infinite, there will be points left over. I pick an A1 from what is left over. Then, if I have picked up to A0 up to AN, then since x is infinite, there'll be still points left over, and I pick an a n plus 1. So I get a whole sequence of distinct. And then okay. And next is for an infinite set. If you remove a finite set, then okay, the size does not change. Well, actually, again, it is a similar kind of thing. That first, x is infinite, so I get a whole sequence of distinct points containing a n plus 1, a n plus 2, I get them all. And then from this a to, I define the map from x to x minus this one by ai goes to ai plus n. So that this portion is taken care of and the rest of the points go to themselves.
Ma'am,
Yes.
what is smallest infinite cardinal? How do I think about it? I mean, is it a constant for that fixed set, or it can be one, or what is it? What is exactly smallest infinity cardinal?
So, well, what is the question? I didn't quite get. Say that again.
What is smallest infinite cardinal, ma'am? I don't know.
What do I mean by the smallest infinite cardinal? Is that what you are saying?
Yeah.
Oh, take n. Oh, it is less than equal to any infinite cardinal. See, Aleph 0 is an infinite cardinal, right? We have already said what are the finite ones. 0, 1, 2, n. These are the finite ones. Okay. At some point I said that. So Aleph 0 is an infinite cardinal. Take any other infinite cardinal. We have said Aleph 0 is less than equal to that.
Okay.
Okay. So it is the smallest infinite cardinal.
Got it. Thank you.
Okay. Okay, this we'll use sometime. I see. This we will be using for the arithmetic sometime. It may have come a bit early on, but since it's here, I will do it here. This is a notation for all functions from y to x. You may be familiar. And if y and z are disjoint, then obviously if I take xy cross xz, what will I get? I'll get pairs of functions going from y to x and then going from, f. I'll get pairs of functions fg, f going from y to x, g going from z to x. And if these are disjoint put together, it will give me a function from y union z to x. And then, okay. Okay. Oh, so here this is the proof. Anyway, this is what I said, and this is the proof. And then, okay, this other, see, this is because later on when you are doing cardinal arithmetic, this is the law of indices will come. This is why this is here. So x to the power y to the power z is x to the power y cross z. Okay, let us see why. So, yeah, I know. So this is the bijection. To any f here, you associate the map yz going to fzy. Fz is a map from y to x, right? So fzy is a map going from y to fz is a map from y to x. So if you think of it as a map of z and y, it is a map going from zy to x. So, okay, I call it yz, doesn't matter. And this is, of course, probably you know already, that 0, 1 to the power x is same as power set of x. By the way, these are cardinalities we are saying. It's not the same sets, any of them. xy cross xz is cardinally the same cardinality as x to the power y union z and so on. It's the cardinalities that are the same. And same here. So what we are giving a one-to-one association. and of course here any subset of X can be associated with its indicator functions.
Hello,
So,
ma'am.
yes.
Can you please go over the proof once again? My internet is a bit bad.
Oh, this whole thing? This whole proposition 8?
Ma'am, the proof.
The proof of proposition 8. Okay.
Yeah.
So what we are saying, so suppose Y and Z are disjoint sets, then cardinality of X to the power Y cross X to the power Z is the same as cardinality of X to the power Y union Z. So what is X to the power Y? It is the set of all functions from Y to X. So this left-hand side is really all pairs of functions fg, f going from y to x, g going from z to x. But since y and z are disjoint, when you put them together, what you get precisely are the functions going from y union z to x. So that is the map. This fg you take to the map f union g, or whatever you want to call it, going from y union z to x. That is the bijection. Okay.
Yeah.
And then similarly, shall I do the others, or have you got
Yes,
the
yes,
others?
yes, ma'am. Yeah, yeah.
Do the others?
Yes.
Okay. So x to the power y to the power z. What does that mean? F is there. That means f z is a map from y to x. Now look at the map G. G y z is f z of y. This gives a map going from y plus z to x, and you can get a one-to-one correspondence of this way, the way it is written, y z going to f z y. So that gives you 2. And 3 is, of course, that for each x, well, this for me is the indicator function of x. For each x, sorry, yes. For each x, the indicator function of a for me is the set of points taking elements of a to 1. So to each subset, you associate the function taking those points to it. So that is your correspondence between power set of x and 0, 1 to the power x. Is it okay?
Ma'am, the last one, the third one, just once again.
Okay. This is it's written the other way around. That's all. Take a function in 0, 1 to the power x. What is it? It takes some points to 1 and some points to 0.
Yes. Yes.
So
yes.
Look at these points that are going to 1.
Yes.
This function goes to that subset of x. Suppose A is the set of points such on which fx is 1. Then this f goes to A. That is your bijection from 0, 1 to the x to power set of x. Is that okay now?
Yeah, okay.
I was saying it the other way around, that's all. Okay, now these inequalities, that cardinality of x is less than the cardinality of power set of x. Now, this means, of course, first is you have to show it's less than equal to, and then you have to show that it is not equal to. Okay, now for empty set, nothing to say. Power set of empty set contains 1 point, the empty set itself. So cardinality of the empty set is 0, cardinality of this 1 point set is 1. Which is okay, which is less than 0 is less than 1. Okay, now so take a x which is not empty. Then the map x going to singleton x is an injection taking x into the power set of x. So this mod x is less than equal to mod power set of x. Okay, now it should not be equal. So there should be, see, if I can prove that there's no map from x onto power set of x, then I'm done. Then there can be no bijection. Okay, so suppose there is such a map, we will get a contradiction. Because then look at, suppose there's such a map f. So every fx is a subset of x. So look at all those x such that x does not fall into fx itself. This itself is a subset of x. So suppose it is fx0. Then where will x0 be? See, x0 will be in A if and only if x0 is not in fx0, that is x0 is not in A. So this is not possible. I'm getting a contradiction by supposing that there's such a map F. So there's no such map F. Okay. That means that we get lots of cardinals. You can start with anything, any infinite one like natural numbers, because we know that.
Hello, ma'am.
Yes.
In the previous proof, why we are not using x doesn't equal to f of x. Instead, we are using the set notation x not belonging to f of x.
What did you say? X cannot be equal to f of x. Wait. How can x be equal to f of
because
x?
f of x maps to only
are you
one
talking
element.
of, wait, are you talking of singleton x? Because
yes.
f of x is a subset. F of x is a subset of x. It's going into power set of x. So it can't be equal to x, which is an element of x, right? Are you thinking of singleton x, the set?
No, if any x singleton, then f will map it to only one element of x, right? So
wait a minute. What is it you are trying to say? You see, what are we trying to show? That there can be no map onto the whole power set. There may be see the singletons. Anyway, there is a map F taking x to singleton, any x to the singleton x, right?
okay. So okay, got it. I think
subset. You cannot get a map taking in all the subsets. That is all.
Okay. Okay. Thank you. I understood.
All right. Is it still a bit confusing?
No, ma'am. I understood it.
Okay. That means, okay, there's no end to it. There are lots of cardinals and you can get as large as you like. We begin with natural numbers. That is aleph naught is the cardinal. You take power set. That is larger. Well, we call it 2 to the aleph naught actually, but okay. And then power set of that and power set of that, and larger we get. And so you can get lots and lots of them. But okay, now we are coming to, see, we did these things with natural numbers, just with that. Now for any infinite set x, most of it can be done. So any infinite set x, we get this. X cross 0, 1 is x. Cardinality. And, well, I should have probably said it when I did it with natural numbers. But suppose I can prove it. What will I get? X cross 0 is the same, is 1-to-1 matching with x, right? X cross 1 also has a 1-to-1 matching with x. So you can actually break x into 2 disjoint sets, each of the same size as x. Sounds funny, but so it is. And then by using induction, you can break it into any finite number of disjoint sets, all of the same size as x. And, well, this is actually something we'll need later. So maybe we go straight to proof of the theorem. This is what we'll need for the next theorem, I think. This is again the similar kind of idea as before we used. We are trying to prove that.
Hello, ma'am.
Yes.
And what is the theorem here?
Oh, the theorem is that look at any infinite set x, and this is the theorem. Theorem 10. For any infinite set x, cardinality of x cross 0, 1 is the cardinality of x. So, and then you can sort of proceed from there and say you can break x into any finitely many disjoint parts, all of the same cardinality as x. Okay. And now we have the proof of the theorem. And it is again a similar idea using Zorn's lemma. You take all AF such that A is a subset of X and F takes A cross 0, 1 to A. Bijection. Now, first of all, we need is it non-empty? Yes, because for any countable set, you will get an F taking any countable A subset of X. X being infinite has a countable subset. Have I already done that? Yes, I have already done that. So any countable subset of X will have an F satisfying this. So this is certainly a non-empty set. And then, as usual, I define a partial order on it by, if BG comes after AF, if B is larger and G extends F. And as before, you will say, see, it has a maximal element. Same Zorn's lemma you use. Any chain has an upper bound and that will be a maximal element. Now, what do we want to show? We want to show, actually, I'm not straight away getting that this maximal element is the whole of X, but I'm getting something of cardinality same as the cardinality of X. That is to say, there is an A, cardinality of A is cardinality of X, and there is a bijection from A cross 0, 1 to A. But this is good enough because in that case, since A and X, there's a 1-to-1 match, for X also, there will be a bijection from X cross 0, 1 to 1. Okay. So it's straight away we get something of the same cardinality. And we get something of the same cardinality by showing that what is left out is finite. X minus A is finite. We have already seen that if from an infinite set you take away finitely many points, the size does not change. So if I show X minus A is finite, size of A will be size of X. So why is it finite? Suppose it is not finite, inside it will be a countable infinite set B. And from D cross 0, 1 to D, there will be a bijection. We already know that. So from A union B to cross 0, 1 to D, to A union D, sorry, you will get a bijection by putting F and G together. And then this will contradict the maximality of A. So that is this result. And the next result will be that, again, like we had for natural numbers, like that, X cross X for any infinite set will have the same cardinality of X. So let us now go back to that thing that I said we'll need later. So here it is. This says that suppose A and X are two disjoint sets and cardinality of A is less than cardinality of X, then cardinality of A union X will be same as cardinality of X. It will not increase. And why is that? Well, this I do not have to say, right? Cardinality of A less than cardinality of X means A matches with a subset of X. So you can get a Y disjoint from X and same size as X containing A. Now, can everybody see that? I hope everybody can see this.
Ma'am, the second line, then there's a Y.
Yes, disjoint from
one?
X. This one, there's a Y. Just a minute. Do you mean this one?
Yes, this one.
That is because, see, A looks like a subset of X, right? So, but A is disjoint from X. Now look at X minus A. Suppose I replace it by some X minus A cross something, just to make it disjoint from X. I can do that, right?
Yes.
And tag that onto A. Call that set Y. Then I'll get a Y disjoint from X and of cardinality same as that of X. Is that clear?
Right.
So that is what I get.
Okay.
Now cardinality of X less than equal to cardinality of X union A is trivial, right? Because X is actually a subset of X union A. And then again, less than equal to cardinality of X union Y, that is also trivial. Now this uses the fact of cardinality X cross 0, 1 is cardinality of X. What does it say? It does say that if I take two disjoint copies of X and take the union, like X cross 0 and X cross 1, cardinality remains that of X, right? What does this say? This says cardinality of x cross 0, 1 is cardinality of x. So that means that if I take x0 and x1, two disjoint sets, both of same cardinality as x, then the union will also have cardinality as same as x. All right. And so here I have x and y, disjoint sets, cardinality same as x. So union will have cardinality same as x. That okay? All right.
Yes, ma'am. Yeah.
Okay.
Beautiful.
And now that says, now this x union A has got sandwiched between two x's. It is less than equal to x and x is less than equal to this. So cardinality of x union A must be cardinality of x. So that is the first thing that we are going to use. Next thing we are going to see here is this. This we have seen. It is theorem 11 that we are going to see. First, so using this we'll see that you cannot have two sets, both of cardinality less than x, a disjoint, actually disjoint or otherwise. And so with the whose union is x, that you cannot have. Because suppose it is so, then okay, look at A and B. One of them must have cardinality less than equal to the other. Say A has cardinality less than equal to B. Then cardinality of A union B has to be less than equal to cardinality of B. We have seen that. Actually, it will be cardinality of B. So, if X is A union B, cardinality of X will be cardinality of A union B. But on the other hand, I have already said cardinality of B is less than cardinality of X. This is not possible. Okay. So, this we cannot have. We are going to use this. Now, use the same idea as we have used before. This Zorn's lemma idea. And look at all AF such that, okay, there is a F is a bijection from A cross A to A. And I think I would like to throw in A is infinite. Because otherwise, okay, you will have problem with singleton which satisfies this and something and suppose. So I think I'll throw in A is infinite. You know that it probably isn't necessary because we are going to take the maximal one, but just to make ourselves comfortable. And you know there are such infinite sets. Since X is infinite, any countable set will have this property, that there's a bijection from A cross A. So look at all such P's and partial order as before. You know, if AF comes before BG, if A is a subset of B and G extends. So same order as before. And as before, there is a maximal element. And again, as before, we want to show that its cardinality is same as the cardinality of that of X. Okay. So, otherwise, cardinality must be less than X because it is this, after all, A is a subset of X. So, cardinality cannot be more than X. Okay. And suppose cardinality of this is less than X, then cardinality of X minus A must be cardinality of X. Because we cannot have two sets, both of cardinality less than X adding up to X. So, in that case, all right, inside X minus A, there would be something of the same cardinality as A, right? Because X minus A is like X and A is smaller. So, and all right. And now I break this B into three parts, again, all of the same size. That we have already seen we can do. Three disjoint parts, all of the same size. Now, since they're all of the same size, everything is like A. So from A cross A to A, there's a bijection means from B cross A to B1, there's a bijection. A cross B2, there's a bijection. You can sort of match them all with A. B cross B2, there's a bijection. And now, putting them all together, you get a bijection from A union B to A union B. Sorry, A union B cross A union B to A union B. And this, since B was disjoint from A, this gives you a extension. This is larger than AF, contradicts the maximality of AF.
Ma'am, can you repeat the last part, please?
Yes. Yes, it is like this. So I know there's a bijection F from A cross A to A. Okay, now B and A are, they are of the same cardinality. That means I can get a bijection from B cross A to A also, right? Now again, A and B1 are of the same cardinality. So I can get a bijection from A to B1. So I can get a bijection from B cross A to B1. Is that okay?
But why are we writing B as this B1 union B2 union B3?
Oh, because we want to get finally this something larger than, otherwise how will we get this something larger than A such with a bijection from some C larger than A with a bijection from C cross C to C?
Larger here means inclusion wise or strictly
No,
bigger
larger means inclusion wise. Larger in that partial order.
Okay. Then can't we just take one?
What's that?
Then can't we just take one element and do this A union singleton, say X cross A union singleton X to
how
A union singleton X?
How will you extend your map F?
Maybe from map F we can do so, because
how will you extend it? Because A union singleton X cross A union singleton X will not be A cross A union X, right? It will also have A cross singleton X and X cross singleton A.
So it's like we have two new copies of A here. And on that side it is just one. Yeah.
And also a point XX.
Yes.
Extra point.
Yeah.
So how will you extend your map? You have to extend the original one, remember. Any map will not do.
Yep.
You have to extend your F. Now here we are extending that F.
Yes, ma'am.
So that is why we are doing this, because this is manipulation only. You have to extend F somehow. So looks like this extends F. I think now we can ask. Otherwise, I think now I will not cover any more today. I would rather you asked any doubts in what was being done. Yes. Now please ask doubts. Any doubts that you had?
Ma'am, just the last proof I couldn't follow.
Okay. So we'll go back to the last. Which one? That X cross X1?
Yes. Where you used BIs and unions.
Okay. We'll come to the BIs.
Wait. No, wait.
Just a minute, please. We are doing it.
You are going
back. Going back.
Yes, ma'am.
Yes.
Yeah.
Yes. Okay. So you want this? You want the proof of? All right. Up to this is okay, that we are looking at all AFs which satisfy this. And then we got a maximal element there. And then we are finding a contradiction. Okay.
Yes, ma'am.
So far, so good? Okay.
Yes, ma'am.
And What is the contradiction? Sorry, just a minute. Sorry. What am I saying? What I said was wrong. We found this maximal element and we want to show that cardinality of this A is the same as cardinality of X. Sorry, what is the contradiction? Sorry, that was a slip. All right. We want to show, yes.
A is a subset of X, right?
Yes, A is a subset of X. So, yes.
And B is what? I mean, B is also a subset, but is there any relation between A and B?
They're disjoint.
Okay.
Where? I mean, when finally the V I get, right? Where? Which B?
I mean, the BG, this B.
Oh, no.
B.
That is, sorry. That is not disjoint. That is only the definition of the partial order. Suppose B is also some subset of X, and AF comes before BG if A is a subset of B, and G extends F. This is simply the definition of the partial order on B. Okay. This is not, the B I get later is quite a different thing. This is simply a definition.
Okay.
And then looking at the maximal element, I wanted to say A has the same cardinality as that of X. That okay?
Yes, ma'am. Yes.
And that is what we wanted to go over. This part?
Yes.
This part?
Yeah. This part.
Okay.
Yes.
So if it is smaller, we get a contradiction. Right? That's what I was trying to say. So if it was smaller, we get a contradiction. How? Anyway, if it is smaller, then what is left over must have the same cardinality as X.
Ma'am, over here, X need not be infinite set, right?
Yes, of course, X is an infinite set.
Okay.
Otherwise, X cross X will not be similar to it, will not have the same cardinality as X.
Yeah.
Yes, X is an infinite set. So that's why what is left over has to have the same cardinality as X. Because if both A and X minus A are smaller than X, then the union will be smaller than X. This is for infinite sets only. Certainly, you can't do this with finite sets. Okay. So, suppose now in this case, since X minus A and X have the same cardinality, and A is a set with smaller cardinality than X, inside X minus A, I can get something sort of equal to A in cardinality. I call that B. Okay.
Right. Yes.
So far, okay. Now, just for the manipulative part, I break B into 3 equal parts. B1, B2, B3. All equal to B. And hence all equal to A. Because I want finally my A union B and some extension of F to be in that partially ordered set. And then I'll say A is not a maximal element there. AF, right? That okay? So I want A union B cross A union B to have a bijection into A. From that, I want a bijection into A union B such that it extends F. Okay? That okay?
Okay.
Have you followed that?
Yes, ma'am, kind of, yes. I mean, over here...
yes, say.
Over here, B, I and A. So A is any finite set or it can be infinite?
No, I made it infinite. I said right in the beginning, let us take it infinite. As a matter of fact, it won't be finite in this case. In the beginning, I said we'll only take infinite sets just to avoid this problem.
Sure.
There are infinite sets that satisfy, we'll take only those. Okay, remember? Okay, so now after having broken this into 3 equal parts, now these A, B, Bi, they are all the same size. So if from A cross A to A, there is a bijection, from B cross A to B1, A cross B to B2, B cross B to B3, whatever, we can put A, B, B1, B2, whatever, there will be bijections.
I mean, ma'am, if they were, I mean, B1, B2, B3, these were not infinite sets, then we possibly won't get bijections, maybe.
We will not get anything if they are not infinite sets. Why are you? But then we have said that cardinality B is cardinality of A. And A is something in P which is infinite. Anyway, so this finite sets question, how does it come? It doesn't come. Is it okay?
Yes, ma'am. Yeah.
The finite, because I began with infinite sets, and now I have said that size of B is the same as size of A. So there's no question of finite sets here. All right.
Yes, ma'am.
Are you sure you are comfortable with this? If you are not comfortable, say so.
Ma'am, I mean, I'll go over it once again. If I'm, hesitant here and there.
Okay, because we seem to have time. So if even today I do not explain, tomorrow I'll explain again. But in whatever time I have, let me try. So if B, A, B1, A, B, B2, they're all the same size, then if from A cross A there's a bijection, I can convert it to a bijection from B cross A to B1 by matching, I first take a map from A cross A to B cross A, or from B cross A to, okay, like that. Or from B cross A to A cross A, I take a map, a bijection. I can do that. Then from that to A, I take a bijection. Then from A to B1, I take a bijection. And I combine this, and I get a bijection from B cross A to B1. Do you follow that?
Yes.
Are you sure you follow this? Because if you follow this, when the same argument, I'll get one from A cross B to B2, one cross B to B3. Because they are all the same size.
Yes, they are all the same size. Yes.
So then, and I'm calling these bijections F1, F2, F3. And I'm calling the bijection from A cross A to A, they already had a bijection F. From there I obtained these bijections. Is that clear?
Yes, ma'am, but how does it contradict the maximality of A?
Wait a minute, I'll come to that.
Yes,
now, when I put this together, do I get a map from A union B cross A union B to A union B, which extends F?
Yes.
You do? Okay. Now, A, if I said was maximal, and this is an extension of that. You see, I have got a bijection from A union, call A union B C. Then I have got a bijection from C cross C to C. Call that G. And this CG then comes into your partially ordered set, and it comes above AF because AF is a part of CG. But AF was supposed to be maximum.
Right.
So that is the contradiction.
Ma'am, then I'm confused in one single thing that we took AF and then we had BG also. So what role was BG playing? Because BG was greater than, in some sense.
No, that was not a BG. That was only a way to define what is the partially ordered relation. That's not a particular BG. It's a general one. Take any BG here in P, we call it larger than AF. That is not a particular set. Okay. All right. Yes, somebody, is that okay? Somebody else raised hand?
Yes, ma'am. I just had a small doubt.
Yes.
Ma'am, in the first line, we have let that like the cardinality of A is less than cardinality of X.
Yes.
So then, shouldn't cardinality of X minus A, A complement in X, be less than cardinality of X?
Can it be? No, didn't we say that if just before that if two sets have cardinality less than X, then the union cannot be X? Didn't I do that just now?
Yes, ma'am. So the cardinality of X minus A should be less than cardinality of X, right?
No. Suppose cardinality of X minus A is less than cardinality of X and cardinality of A is less than X, then cardinality of the union becomes less than X.
Oh,
right?
yes. Okay, ma'am. Yes, I got it. Okay.
All right.
Yes, ma'am. Thank you.
I'd like to remind that there is only 2 minutes left.
Okay,
thank you.
So I'm as such done unless.
Yeah.
Excuse me, ma'am.
Yes.
I had a doubt regarding this notion of cardinal numbers.
Yes.
So it was regarding like their correlation with ordinal numbers.
That I think, what kind of doubt? Maybe Bivira will do that later.
I mean, the thing is, up to the finite numbers, the two sets do coincide. But I wasn't sure if we can say the same thing about the transfinite cases. I
No,
mean,
not all ordinal numbers will not be cardinal numbers. No, there are some
No,
special ones. Hopefully, Bivira will do it. I think he's going to do it.
Okay.
Okay. Okay. But it's no. But yes, I think time is more or less up. But anything more?
Are there any more questions from the participants?
Hello.
Yes.
Hello.
Yes.
Ma'am, if you like accept the existence of classes, then you could actually define cardinality to be the set of all. I mean, you could define the equivalence relation of a numerosity, and you could actually define the cardinal number of set to be the equivalent class, right?
Yeah, probably. But so what?
That is not precise.
Yeah, I don't exactly know what you are saying, but
Bivira will.
But I think Bivira will do these things.
Okay, ma'am.
Okay. All right.
Okay, thank you so much for the lecture, ma'am. We'll take a break of 15 minutes and then we'll come back for the next lecture. So see you then.
Oh, all right then. Thank you. Oh, what will I do tomorrow? Oh dear, I should have slowed down. Yes. What will I do now? Tomorrow go over it again.
Yeah, I will think so little bit more.
I do cardinal. Yes.
So far you have done. So anyway, today you do and tomorrow you do the
think someone is frozen on the screen. I thought I was frozen.
I think it's a photograph being put there. I don't know.
No,
It
I don't
seems
think
like.
it's a photograph. So
I
he
see.
had his video on.
Okay.
I think people are having tea or coffee. We can
Yeah.
wait for a couple of minutes.
Yes.
Hello, sir.
Yes.
Uh, can we ask you questions about, let's say, from the whole lecture after you've
Yeah.
completed?
Of course.
Not now, because I'm not able to, this is a pretty honest thing that
Mm-hmm.
I'm not able to study what you're teaching right now because of lack of time. So I'm planning
Okay.
to do it a bit later. So can I ask the questions later on?
Later in the sense?
Later in the sense, maybe just 1 or 2 day. Let's say not today, but next day.
Yeah, fine. Any time is fine.
Thank you.
I have also responded to a few emails yesterday. So that is also a way to contact me.
Thank you, sir.
Yeah, I mean, I know it. Like for any participant attending an intense school like this, yeah, you can hardly eat and sleep. If you are serious about learning everything that is being taught, yeah, then it is difficult. I was a student not many years ago.
Thank you for understanding, sir. Thanks
Yeah.
a lot.
Yes, I could. Last day you said it took 30 years to come up with the definition of the groups. Yes. Oh, that I don't know any particular book as such, but what should I say? I mean, I can try to look for it. That's the only thing I can say for now. Dhruv, you want to say something?
Yes, sir. Sir, so like any mathematical proof we do,
Mm-hmm.
can we translate it into the language you developed for us yesterday?
I mean, not every mathematical proof. There are some limitations, of course. So what we have seen so far is just the logic of connectives.
Okay.
So in today's lecture, we will see what is meaning of first order logic. And then I will also briefly explain what we cannot cover using first order logic. And once you understand all those things, then together, yeah, using higher order logic, you can definitely argue. But you have to compensate for that by leaving out the compactness and completeness properties. I mean, it will be, yeah, it will be clear very soon.
So can I ask something?
Yes.
Sir, if we don't convert every proof into, like, suppose there is a very long proof, right? Say some 200 pages proof. There are a lot of proofs, right? So how do you check that whether a proof is correct or not? Like, it is written by a human, and if a human is checking it, it can
Yes,
be
so
wrong.
there have been many instances in the history of mathematics that people assume that the proof is correct for a long time, and after around 100 years they have found out mistakes. Yeah, so nowadays, because of thanks to Vygotsky and other people who are working in homotopy type theory and computer science, like kind of intersection, so people are interested in automated proof systems. Yeah, so or proof checkers. So you can write down a proof and then the proof checker will verify whether it is correct or not.
That means in that proof we cannot use any word, right? I think like everything has
Well, I
to
mean,
be.
it depends on how good your computer program is to understand that.
Well, okay.
Yeah.
And so on the question that I asked, that like on the
Yeah.
definition of groups, I don't see any book, like all the textbook starts with the definition of group, right? And any other math, they like most of the
History
math.
of mathematics could be the way to go for, but yeah, I'm of course not an expert in this area, so.
Well, so like, I believe without knowing the history, like it's not like I really to really understand the what's going on. I think I should know how it developed. Otherwise, like it is like I slept and then next morning I woke up with an set of axioms, and I start working there.
Right. No, I mean, you can have a general feeling for that by just thinking about the definition, that how a definition is arrived at. You have to think about a class of examples and you want to find some common properties. If time permits, I will say something more about it in the last lecture.
Right. Okay.
Yeah. And yeah, I think there are many more questions, but yeah, the host is waiting to start the meeting. Let me give him the opportunity. I have already started essentially.
Yeah. So I'll formally start the talk. So welcome to the third talk in the series by Dr. Amit S. Kuber. He'll be continuing his lecture on completeness and compactness theorem in propositional and predicate logic. Over to you, sir.
Thank you. What's your name?
So I'm Swapnil Tripathi. I'm a PhD student in IISER.
Yeah, thanks. Yeah. Thanks, Swapnil. Yeah, so yeah, are there any questions from what I covered yesterday? I mean, let us leave out the philosophical questions for the tutorials for now. Then, I mean, I'll just have a look at the chat once. Yes, if there is if in the sequent notation, if there is nothing on the left hand side, it means empty set of propositional formulas. Then Agnivo, we can talk about it in during the tutorials. Then Arul, okay, yeah, this is not related. This is not a question as such. Any other questions from the material that we saw yesterday? Okay, if not, let us quickly recap. So we saw two versions of completeness theorems yesterday. Yeah, first one said that if a set of propositional formulas is consistent, which means it cannot prove formally a contradiction, then that set is satisfiable, which means there is a valuation V which makes every single formula in that set true. Okay. Second version, which actually looked like the converse of soundness theorem, that if T is a logical consequence of S, then there is a proof of T from S. Yeah, there was a question from one of you in an email that why is this proof not constructive? So anything which uses axiom of choice, if you have paid close attention to axiom of choice, it only guarantees existence of something without explicitly constructing that object. Yeah. So therefore, in this proof, we use Zorn's lemma. It guarantees existence of a maximal subset of maximal consistent extension of S. And based on that, we constructed a valuation. But we don't actually know what that maximally consistent subset looks like. We don't have an exact condition, as in this particular formula belongs to this set, this particular formula doesn't belong to this set. We just know about its abstract properties, that only one of T and negation T can belong there, and so on. Yes, Ramakrishnan?
So this compactness theorem, adjacent to whatever is there in the bracket, purely semantic equivalent of completeness. So completeness, it says T T logically follows from S if and only if T you can prove it formally from S. So how is this statement it's satisfiable if and only if finite? How is it that it's the semantic?
Yes. Okay. I mean, this is at a much higher level.
Okay.
Yeah, I haven't yet started talking about compactness. I will come there.
Oh, okay.
Yeah, I'm still talking about completeness. But anyway, so what my point was here, that if T is a logical consequence, then there exists a proof. But the proof of completeness theorem doesn't actually produce this proof, this formal proof of T from S. Okay, so in this sense, it is not constructive. It just guarantees existence of one, but it is not constructive. So whenever axiom of choice cannot be avoided, then such a mathematical statement is not constructive. There is a branch of mathematics called constructive mathematics. Yeah, so those people will first throw away axiom of choice. They will also throw away something called the law of excluded middle. Yeah, so there are many other things, and there are many questions which can be answered in some non-classical logics. So intuitionistic logic is one of the ways to approach constructive mathematics. So there is a lot of literature available. What we are doing here is classical propositional logic, which has Boolean logic as its base. Yeah. Okay, so now I will start with compactness theorem, that it is a purely semantic equivalent of compactness, in the sense that I explained yesterday, that completeness theorem is an equivalent of a weaker version of axiom of choice. Yeah, that statement is called Boolean prime ideal theorem or Boolean prime filter theorem, that every filter can be extended to an ultra filter. So completeness theorem is equivalent to Boolean prime ideal theorem, and compactness theorem is also equivalent to Boolean prime ideal theorem. And in that sense, these two statements are equivalent. So let us have a look at the statement. So here we are saying that a set of propositional formulas is satisfiable if and only if each finite subset of S is also satisfiable. Yeah, one side of it is trivial, that whatever is the model of the full set S, that is also a model of every finite subset. So that is trivial, but how to show the converse? Now the converse is the semantic equivalent of the finite character of a proof. And we are exactly going to use this finite character of a proof. So suppose S is unsatisfiable, then by completeness theorem version 1, S is inconsistent. Then we can prove a contradiction. We can arrive at a contradiction, a formal proof of a contradiction from that. So that is negation S implies S. Now, because of finite character of proofs, because proof is a finite sequence of sequence, there is a finite subset, say S naught of S, which also proves this contradiction. And because this statement is if and only if, so we conclude that S naught is inconsistent. Yeah, and S naught is inconsistent by soundness theorem, S naught is unsatisfiable. A very simple proof from here, but in predicate logic, the next part that I'm about to start, we will see an independent proof of compactness theorem, and we will leave out completeness theorem from our discussion. Okay, so any questions about this? You can directly ask, no need to raise your hand. I mean, with this theorem, we have finished the syllabus of propositional logic, and There is a tutorial sheet already available on the website. You can try out during your lunch break, and we will discuss the solutions in the tutorial session. Okay, if nobody is talking, I can start talking about first order logic or predicate logic. Yeah, so we are going to expand our language so that it will have more expressive power. So far, what we said that, okay, mice like cheese. Yeah, this is a statement that we don't go into its construction. We don't go inside it, how we constructed that. But suppose you want to say mice like cheese, cats like cheese. So liking cheese is a property, is a predicate that you want to abstract, and then you would like to say, okay, likes cheese bracket mice, likes cheese bracket cats. So you want to make some statement about elements of a set. Yeah. So that is how we are going to approach this first order or predicate logic. So let us first start with the alphabet as usual. The alphabet here is negation, conjunction that we already had. Yeah, this is the logic of connectives. Then we also had parenthesis. Now the main thing that we are going to add here is the existential quantifier. Okay, so this is the main object: existential quantifier, universal quantifier, and we will soon explain what is its importance and what is its scope. What exactly we can do with this. Yeah, and we also need a countably infinite set of propositional variables available to us. And actually, I mean, I can rephrase this. So whenever I require a new variable, I should be able to access that new variable. And just to be pedantic about things, I have classified them into two parts. Like I will say free variables, I will denote by letters X, Y, Z, and bound variables, I will denote by letters W. Okay, just to distinguish between these. And once you get used to these things, then there is no need to talk about this distinction. You can freely use any symbol for any type of variable. Okay, then there is something special here that we also add the equality symbol in our meta language. So the technical term for this is that whatever structures we are going to consider, they will be normal structures. So equality symbol will also come with some properties. Yeah, like equality is an equivalence relation, and it behaves nicely with respect to the language that we have. Yes, Shashank?
Sir, so the equality symbol that you have taken, it has two dots also. So
Yeah,
is it?
I just wanted to distinguish between the normal equality that we use in a set and equality used as a symbol.
Okay.
Yeah, I hope it's not too confusing for you.
No. Thanks.
Yeah. Then we also have some other symbols available to us, and they will be abbreviations as we discussed earlier. So disjunction will be negation of conjunction of negations. Implication we know, by implication we know, and we have one more symbol, which is the universal quantifier, which is the abbreviation for negation. There exists negation. Okay, so once again, we need unique readability, and for that, I'm only going to start with only three symbols: negation, conjunction, and existential quantifier, and the rest of them are kind of derived symbols or short forms. Okay, so yes?
So can you again explain why we need first order logic or predicate logic? Means what is the drawback of this proposition logic? So we need this.
So we want to have more expressive power. So, I mean, yes, let us wait for some time and you will soon understand its importance.
Yes, like you in the starting you said some example, English statements. What can you repeat it?
So, like I said that mice like cheese.
Yeah.
Okay. So suppose liking cheese is written as property P.
Okay.
So what I'm saying that for all x ranging over the set of mice,
Yes.
P of x is true. For all x px, where
Okay.
x is ranging over the set of mice. But I can also say for all y, I mean for all x px, but x is ranging over the set of all cats. Yeah, that is so this for all x, like I can distinguish between mice and cats now. So earlier what I said that we cannot go inside the construction of statements or propositions that we started with. Yeah, mice like cheese is just treated as a propositional variable small p.
Yeah.
And you stop there. But now we can go inside and say something more about it. Yeah, we can perhaps understand a bit more.
Okay.
Yeah, so this language is going to help us to do that. So our language consists of some constant symbols. So const is the set of constant symbols. Rel is the set of relation symbols. Fun is a set of function symbols. Like right now, these are just symbols. Yeah, they don't mean anything. And arity is a function from rel union fun to natural numbers. So here by natural numbers, I mean 0 included. So right now, these are just symbols, and associated to each symbol in these two sets, we have a natural number, which we call as an arity.
Amit,
Yeah.
since I will be following you, can you just lower down this page little bit?
Yes, I'm doing that.
Lower it down,
Oh, here.
Here. Now, within parentheses, these will be defined symbol. This is not the part of your meta language, right?
Yeah, but you can freely use them.
No, but that is what you are saying. That is what you have said. I need that. That's all.
Okay.
I mixed that part. I had to go.
Okay.
Yeah. Go ahead.
So now a structure for this language L or an L structure is a tuple of this kind. So it consists of a universe of that structure followed by some interpretations for each one of them. Yeah, everything written in L. So what is this? M is the universe of that structure, which is a non-empty set. Yeah, non-empty is important for our purposes. Then for each constant symbol C, there is an element Cm in M. Okay, so each constant symbol is actually interpreted as an element of M. Which element, that doesn't matter. Yeah, it is just an element. To give an L structure, to give an interpretation for L, yeah, we just need this data. It is just part of this data.
Sir?
And for yes?
Sir, can you repeat what the tuple is? This tuple? M.
Yes,
M
so this
is...
tuple is what I'm describing. Yeah. So M is a non-empty set. Then for each constant symbol, I have an element, a specific element chosen from M. Then for each predicate symbol R, we have with arity M, we have a subset of M to the power M. Yeah, so as SMS has mentioned in his lectures, what is a predicate? Predicate is a logician's way of talking about relations. So R is a relation symbol of arity M. So we are just taking an M-array relation. So a relation symbol is interpreted as a relation with same arity. So for example, what we were doing, like to like cheese, yeah, the property P that we were talking about, that is a unary predicate. So a particular mouse might like cheese or it may not like cheese. So the collection of all those mice who like cheese, that is the interpretation of the set of mice. Okay, so this is how we are interpreting it. And
Sir,
moreover, Yes.
So like the, I mean, what constitutes the tuple M? What constitutes the tuple M?
So
M
it
is,
is this data. It is the data that we are describing here.
okay.
Together,
Okay.
like M together with the collection of CMs, collection of RMs, and collection of FMs. That is the data that constitutes the tuple.
Okay.
And actually, you are familiar with this. Once I talk about examples, it will be suddenly clear to you. And for each function symbol f with arity n, we will have a function from m to the n to m. Okay, fm is a function from m to the n to m. That's all. Okay, so let us not go into these abstract details immediately. Let us look at the second example.
Just a small thing. What is
Yeah.
m to the 0? If the parity turns out to be 0, what is m?
Yes, what is m to the 0? So just today you saw in cardinal arithmetic, what is meaning of a to the b, where a and b are two sets?
The functions of all.
The set of functions, correct. Set of functions from b to a, that is a to the power b. So 0, as Professor B.V. Rao described yesterday, 0 is the empty set. So empty set to m. So m to the 0 is the collection of all functions from the empty set to m. Now, a function is a triple. It is collection. It is the triple consisting of the domain, the codomain, and as well as the graph of the function. Okay, so empty set comma m comma a subset of empty set cross m. But empty set cross m is empty set. And the only subset of that we can talk about is the empty set itself. And that empty set satisfies the property of being a graph of a function. That means for each element of the domain, there is a unique element of the codomain. And therefore, there exists empty function. Yeah, this is called the empty function from the empty set to m. And that is what m to the 0 is. And there is a unique such function. The empty function is the unique function in the set m to the 0. So what you need to know that m to the 0 is a singleton. It consists of unique element. That's all. Yeah, I said this yesterday as well. I said it today again. So can we go to the second example now? Yeah. So we have got one constant symbol in our language. This is the language for groups, let's say. One constant symbol, then no relation symbol, and one binary function symbol. A binary means arity 2 function symbol. Then what is an LGR structure? It is M, comma, the interpretation for this symbol, yeah, that is just an element of M. And the interpretation of this binary relation function symbol is a function from M squared to M. And for example, R0 plus is an LGR structure. So where this star is interpreted as plus, but so is R0 dot. Yeah, dot is also a binary function on real numbers. 0 is some specific element. And natural numbers with addition are plus with multiplication and 1. So there are various possible structures. You can actually interpret this star as any function on pairs. Yeah, any function from m squared to m.
Sir?
There is no restriction. Yes.
So this, capital M semicolon e to the power m. So this capital M is this non-empty set that we talked about, right?
Yes, that is the non-empty set.
Okay.
And em is an element of m. Yeah, so we
Yes,
want to guarantee that there exists an element. If there are constant symbols, then they are interpreted as elements, and therefore we should have that the set is non-empty.
Yes, sir.
Yeah. So let us go to the first example now.
So, Is the operation should it is necessary to be a binary operation, whatever the operation we are choosing?
No. As I said here, it could be any n arity operation, n array symbol. So n is any natural number. As we have described here, arity is a function from rel union fun to n.
Okay, so my operation should only be on M. I can't choose anything else outside of this.
No, you can't choose anything else. Yeah, it has to be from m to the power something, some natural number to m.
Thank you.
It can start with n inputs, but it has to give only one output, and that output has to be an element of your universe. Yes, there is one more question in the chat, and why don't you talk? That's better. Dhruv? No, there is no restriction on cardinalities of rel function, etc. No.
Excuse me.
But we are requiring it to be a set.
Excuse me, sir.
Yes.
Sir, here is this structure that you're calling LGR structure. Is LGR structure a standard terminology?
Sorry, I couldn't hear you. There is some disturbance.
Am I audible now, sir?
Yeah.
So is the word LGR structure a standard terminology for structures of this type, one constant symbol and one arity to relation symbol? I mean function
yeah,
symbols.
I mean, you can define. So this GR, it just stands for groups. Like this is my notation.
Yeah, that was my doubt, sir, because here in the examples we have given N0 plus, and N0 plus is not a group. So I was thinking,
definitely. I mean, it is just the language of groups. And I mean, the main point of defining it as GR was also that you don't need to have any. So groups are not relevant here. We are just trying to abstract out the properties of the structure.
The symbols.
Yeah, the symbols, yeah.
Okay,
the symbols just mean that for a group, you need a binary operation. And you need a constant symbol which will play the role of identity. That's all. And yeah, perhaps you can also add one more unary function symbol which plays the role of inverse.
Yes, sir.
Yeah. So yes. And the main point of writing R0 plus and R0 dot is that we are not talking about properties of those structures yet, not talking about the axioms. Like with respect to multiplication, 0 is not the identity, but we have never talked about something being identity, like writing down the axiom which says something is identity.
Yes, sir. We are just
so
defining
far,
the
we are
symbol.
just talking about what is the bare minimum to define a structure.
Okay, sir.
Similarly, if your L set happens to be empty, I mean, if your language happens to be empty, like no relation symbols, no constant symbols, no function symbols, then L set structure is just a non-empty set.
Okay, sir.
And L-ORD structure, let's say ORD stands for ORD or some order relation, and it's in like this language consists of just one binary relation symbol. So this structure is nothing but this pair, a set, comma, a binary relation. Yeah, relation symbol is interpreted as on M. For example, R less equal and strictly less than. So there was a lot of discussion yesterday about less than or equal to and less than. These are both valid L-ORD structures. And ORD just doesn't stand for order. Yeah, a non-empty set with an equivalence relation could also be thought of as an L-ORD structure. Because equivalence relation is also binary relation, and that is all we care about right now. We are not talking about any axioms or properties so far. Yeah, and one last language that will be useful. Yeah, L-ring. It is the language which consists of two function symbols then 3 function symbols, 2 constant symbols and 3 function symbols with arities 2, 2 and 1. And these are the standard structures which all of us understand. We can of course also mix them. Yeah, Z has an order, R has an order, yeah, less equal. So we can include them here and we can just include that in this empty space here.
Sir?
Yes?
Sir, in the L ring, the third, this one. So this is like the symbol of minus, the one, yes, the one-ary function. So this is not minus, you mean, right? I mean, just a one-ary function.
It is just a unary function symbol for now. Yeah, and this is not A minus B. I'm not treating it like A minus B. A minus
This
B
is something like the successor function, you mean? Something.
No, it could be successor function. It could be just the minus function which takes any integer to its negative.
Right.
Yeah, it could be successor function also. It could be predecessor function in the case of Z. It could be anything. Interpretation is totally up to you.
Yeah.
It should be just a function from the universe to universe.
Sure. Okay.
So that's why what I said, like we want to separate out several things. We want to separate out structure from properties. And that is the goal of this first part of predicate logic. Yeah, as somebody already asked and I answered, that constant symbols could be thought of as zero-ary function symbols. Because in that case, what happens, like this m to the 0 is a singleton, and from that singleton, you are taking a map to m, which means you are choosing one element of that. And yeah, so some authors prefer not to talk about constant symbols separately. Then zero-ary relation symbols, yeah. So zero-ary function symbols have a special name. Yeah, those are constant symbols in our setting. But zero-ary relation symbols are actually propositions from propositional logic. So how exactly that is the case? That if it is a zero-ary relation symbol, then it is a subset of m to the power 0. M to the power 0 consists of just one element. So this relation symbol can be interpreted as a subset of a singleton. So there are only two choices for a subset of a singleton, either empty set or one, or the entire singleton. So empty set can be treated like false and singleton can be treated like true. So essentially it is a valuation. Yeah, and a predicate symbol of arity m is a propositional variable. That is what I'm trying to say here.
So can you again explain the zero-ary relation symbol, how it is proposition?
Yeah, so zero-ary relation symbol is just a symbol which has arity 0. And what will be its interpretation? It will be a subset of m to the power 0. M to the power 0 is a singleton. So there are only two choices for a subset, either the empty set or the singleton set itself. The empty set can be treated as the truth value, false, and the full set can be treated as the truth value, true.
Yeah, okay.
So its interpretation is either false or true. So that is what we mean. Yeah. Okay. So
if we don't have any functions or any m-ary relations for m bigger than 0,
yeah,
then can we and we don't use any existential quantifiers, then can we say that we are doing as good as we were doing in the propositional logic?
Yes, this is how we can think of PL as a fragment of FOL. Yes, that's precisely my next statement.
Oh, yes. Okay, thank you.
Yeah. So FOL provides a way to talk about relational and functional algebraic structures. Yeah. So these are like, I'm also treating relations as being algebraic in some sense. Yeah, here I cannot talk about topology for those who know topology. And when I will come to interpretation of this there exist and for all symbols, I will say more about this. Just hold on for that. Okay, so
what do you mean by this relational and functional algebraic structures?
So, like in groups, we have operations. Yeah.
Okay,
Those
so
operations are
structures
finite
like these.
operations, and relations also are finitary. Yeah.
Yes.
We are not talking about arbitrary arities, only finite arities. So, the full description of this logic is finitary first order logic, which is denoted by L omega omega, where finitary refers to finitary conjunctions. Yeah, we cannot have arbitrarily long, yeah, like infinite conjunctions are not allowed. That is what the first omega refers to. And the first order refers to quantification over elements rather than subsets of the structure. Yeah, so this I will make more precise when I describe the interpretation of quantifiers. Okay, so we have included the equality symbol in the meta language, and thus our structures are called normal structures and equality. And we also add some meta level axioms to ensure that equality behaves in the way it should behave. Yeah? Let us not go into those details, otherwise it could confuse some of you. If you want to talk about it, we can talk separately. And yes, as I said earlier, so for all is an abbreviation for negation, there exists negation, and we will use this symbol freely, just like disjunction, implication, and by implication. So this is like the bare minimum of the languages and structures. Do you have any more questions? Okay, so now let us consider this structure. Yeah, R plus minus 0, 1 less equal, the ordered field of real numbers. Okay, I'm not going to show you the next part yet. And I want to have some conversation with all of you. So what do you understand by a polynomial? Anybody can unmute themselves and talk, but just don't talk with each other. What is a polynomial? Infinitely many variables. Yeah.
So one way can be to like consider it as vector with the basis as x to the power I, let's say. I
Okay.
is natural number.
But in multiple variables, like let's say 2 variables.
I mean, any tuple of finite length. Of course, we'll have to define a specific multiplication.
Okay, you are talking
Yes,
more about it from the interpretation perspective, but as a formal expression, what is a polynomial? Does it say anything?
Some n-ary function symbol, say plus. So the inputs are say x, y. So the polynomial is just the output of the.
Okay, for you, I mean, I will shorten your answer. For you, a polynomial is like a function.
Yeah.
Right. For anybody else?
A polynomial is just an expression consisting of some constants and some variables. Nothing more.
Okay. It is nothing more than that. It is just a formal expression for you, Soumya. Anybody else?
We can also think of polynomials as functions from finite sets to a given set X. So
Finite
like
set.
Yes, so we can take a finite. So we can take the finite set 1, 2, 3, etc. n, and the image of k in this set is the coefficient of x to the power k in the polynomial.
Image of k in this set is?
I mean, I'm talking about a function from.
Oh, you are again treating it like a vector, yeah, as a function.
Oh, okay.
Okay, fine. And any other answer?
Sir,
yeah, first Nitish and then Rupakatha.
So we can see this in this language interpretations, like 1 plus x square, they are different arrays, relational symbols, and our constants are their multiplications. We can see it like that.
Okay, good. Rupakatha?
Sir, mine was just what you in line with what you said. So you talked about X and Y, so maybe we can talk it like let's say a matrix. I mean, what to
Okay.
say?
Matrix of coefficients, perhaps?
Yes.
Yeah, but again, you are resorting to commutative polynomials. Yeah, I mean, it could happen that xy and yx are two distinct polynomials. But anyway, fine. Shivani, one last answer. Yeah, we are not taking more answers.
Yeah. So it is a function from say some r raised to r n to r means like some.
Okay, okay. For you also, it is a function.
Yes.
Yeah. So let me just remind you that we have a countably infinite set of variables available to us from the meta language. Yeah. And now let us define what is a polynomial. So a polynomial px1, x2, xn with integer coefficients can be written as a formal expression which we'll call a term, starting with variables and constant symbols and iteratively applying function symbols. Okay, so x square plus 2x minus 1 is nothing but this expression. It is the addition of these two things. The first one, the first argument is plus of the it is the addition of multiplication of x with x and addition of x with x. And the second component is negation minus of 1, where 1 is a constant symbol. So this can be treated as a term, like we are starting with variables. Yeah, look at the innermost arguments. The innermost arguments are either variables or constant symbols. And we are iteratively applying these function symbols.
Sir?
Yes?
So what would happen? I mean, I can kind of get the iteration, but like let's say x cubed, then multiplication is a binary.
Yes, so you will say multiplication of x comma multiplication of x with x.
Right.
And you will have to add that x square times x is equal to x times x square in somewhere. Yeah, some associativity should be added.
Okay.
Yeah.
What is the leftmost plus for? Leftmost plus is it needed or?
Yes, the leftmost plus is needed to add x square plus 2x and minus 1.
Then the next.
It is associativity that we use when we write this expression.
Then the second plus, doesn't it take care of adding these three? The second.
No, this.
Yeah.
The second plus takes care of addition of x square and 2x.
Oh, okay.
Whereas the last plus takes care of x square plus 2x and minus 1.
Yeah, okay.
Yeah.
Sir?
Okay. Yes.
Or is it like this that, I mean, I'm defining, let's say, plus x squared as a separate term, plus 2x as a separate term, and minus 1 as a separate term, and we are adding all of those using that plus.
But you have to add in a particular order. If you don't have associativity, you have to choose an order in which you add them.
So then the comma separates it, right? Like the first term is separate, the first term comes before the first comma, and then you get the second term. Can you get me?
I can't hear you. Your voice is not there.
So hello?
Yeah.
So what I'm saying is that the plus outside takes care of everything. I mean, adding all those pieces up.
It cannot
each of the pieces.
take care of.
Okay.
It cannot take care of more than 2 arguments at a time.
Okay. Yeah.
Yeah. Okay.
Yes.
So.
Hello.
Yes.
So here we talked about the symbols, fine, but when we have to apply the associativity here, so where would we be, like where would it fall on, like
wait Agnivo.
because it's a property, right?
Yeah, wait for that. Yeah, let us do it step by step. Yeah. So let us go to the second concept now. A polynomial equation or inequality can be written as a formal expression which is known as an atomic formula, that is of the form either apply the equality symbol or the less equal symbol on a pair of terms. Okay, so you can say that polynomial x is less equal polynomial y. So that is an atomic formula. So again, it is a formal expression, just like a term, but now we are using relation symbols, like we are treating equality as a binary relation symbol. I mean, it is a binary relation symbol, but we can use it. So it is either of the form equality applied to two terms or an n-ary relation symbol applied to n terms. Okay, so again, it is a second type of formal expression which we are calling an atomic formula, and it doesn't mean anything as yet. Okay, then the next thing is that a finite system of polynomial equations or inequalities is a finite Boolean combination of polynomial equations or inequalities. Yeah, I mean, we are just talking about conjunction, disjunction, and negation or implication or whatever we could do in propositional logic, and we apply those connectives to atomic formulas. What we get is a quantifier-free formula. And finally, a formula is an expression that could also use quantifiers. So phi0 xy, yeah, just read this out. There exists w, x is equal to w dot w plus y. So can you explain, can somebody explain to me what this formula is trying to say? Yes?
Amit, I also call quantifier-free formula open formula.
Okay. So a formula, yeah.
I think we are trying to get, square root of x plus y over here.
Square root of x
Sorry,
plus y?
X minus y. X minus y.
Are we trying to get the square root, or what exactly are we trying to say here? So phi0 xy, what does it say about x and y?
That x minus y is of the form like w square for some.
Okay.
So it's like given x and y, if there exists such a w.
Yeah.
Then
can you interpret it in some different ordinary language?
Yes, sir. Why?
In real numbers only. Yeah, in real numbers only.
Y is less than x. So
yes,
when we,
y is less equal x.
yes.
Yes, so we are simply writing an expression which makes a statement about x and y. Yeah, there exists a w such that x is equal to w dot w plus y. But again, this is just a formula. It still doesn't have any meaning whatsoever. It is just a formal expression. Okay, now let us come to interpretations. A polynomial or a term, that term will be a generalization of a polynomial. So px1, x2, xn, it actually gives a function. So PR is a function from R to the n to R that sends an n tuple a1, a2, an to the evaluation of the polynomial at that n tuple. Okay, so now we are interpreting a polynomial as a generalized function. Yeah, function symbol was interpreted as a function. Similarly, a term will be interpreted as a function. And this is how we do it. It is evaluation of that polynomial. And we all know what this is. Yeah. Then a formula now. A formula phi x1, x2, xn gives a subset of R to the n. So if there are n variables, it is an n-ary relation. Its interpretation is an n-ary relation. So just like relation symbol gave you a relation, an n-ary relation, so a formula will also give you an n-ary relation. And what it is trying to characterize, it is talking about a specific subset of R to the n, which is given by all those tuples where phi is true in R. Okay, we still don't know what is meaning of phi is true in R, but you can guess that for this particular phi 0 that we had, phi 0's interpretation in R is all those pairs where A1 is bigger equal A2. Our job is to formalize this. Yeah. So a formula is interpreted as a relation, a term is interpreted as a function. This is something which you should never forget. A formula and a term, they both are just formal expressions. They don't mean anything. That is just the purely syntactic part. Whereas these interpretations give you some meaning. That a term is interpreted as a function and a formula is interpreted as a relation. Okay. And finally, a sentence is a formula which does not have any free variables. Like here we said phi of x1, x2, xn, but yeah, it doesn't have, in that formula, these x1, x2, xn do not appear at all. So for example, there exists w such that p of w is equal to 0. This does not have any free variable, which means that every variable that occurs there is bound by a quantifier. So this is a sentence which states that the polynomial px has a 0. Correct? It is a polynomial in one variable that has a 0. But the important thing is that you don't have to substitute. Yeah. There is no way you can substitute in this. It just says, it makes a statement about that structure. That there exists w such that p of w is equal to 0.
Sir? Over here, x could be a tuple also.
Where?
P of w equals 0. So this w could tuple also.
No, I mean, I'm just talking about a single one right now. I mean, I could have said that there exists w1,
Okay.
there exists w2 such that p w1 comma w2 is equal to 0. Yeah? Here I was just using one variable. Yes, Dhruv?
So sir, a sentence is zero-ary?
Yes, sentence is a zero-ary relation symbol. A generalization of a zero-ary relation symbol. And just like we saw, what is a zero-ary relation symbol? It is a propositional variable. So what is its interpretation? It's a valuation, either true or false. So similarly, we can assign values true or false to a sentence. Correct. Very good. So in summary, we have this following picture. And this you should never forget. Like I will give you all the formal definitions, but this is what you should remember. A term, a formula, and a sentence are purely syntactical objects. For a term and a formula, you need to describe how many variables you are using. Then a term is interpreted as a function, n-ary function, and the formula is interpreted as an n-ary relation, which is also known as the set defined by that formula or a definable set. But a sentence in particular, which is a zero, like it doesn't need any number of variables. So a sentence is interpreted as a truth value. So it will be either true or false. It is a zero-ary relation on your structure. And by making it zero-ary, the advantage is that it loses its dependence on the universe. Yeah, here it is a subset of m to the n, but m to the 0 is same as m prime to the 0 for any other non-empty set or any empty set as well, but we don't care. So this is the picture that you should remember. And I also want to point out by talking about these notations, like let's say the terms are called TL, formulas are called FL, and the sentences are called SL. And this agrees with our notation in propositional logic that propositional formulas were named SL. Okay, because they were just sentences. They are atomic sentences. They don't even have any quantifiers. That is why atomic. Any questions so far?
You said they don't have any quantifiers, but a sentence can have a quantifier like this.
Yeah. Like propositional formulas stated
Okay.
as sentences do not have any quantifiers.
Yes.
Yeah, they are atomic sentences.
Okay.
So here,
yes.
Yeah, Dhruv?
Sir, but when we want to ensure there is no free variable, you have to bound it by a quantifier, right?
Yes, but there are no free variables. See, there is a difference between a propositional variable, which is a zero-array relation symbol.
Oh, so that in itself, so we
Yes.
don't need to go to the syntax of that sentence. It is just
Yes.
anything.
Yes. Zero-array relation symbol is separate from a variable that we are using in first-order logic.
Yes. Okay, so sir, if I have a term with only constants,
yeah,
then it is also a sentence.
No, a term doesn't make a statement.
A
It is
formula.
A formula with only
constants.
Yeah, I mean, that is called an atomic sentence.
Yes.
Yeah, for example, if you say C1 is equal to C2.
Yeah.
Yeah, that is an atomic sentence, correct. So just to recall once again that a term is a polynomial, a formula is a polynomial inequality or equality, maybe more complex with like it's Boolean combinations like conjunctions, disjunctions together with quantifiers. A sentence is a statement, yeah, which doesn't have any free variable, no chance of substitution whatsoever. This is a polynomial equation, polynomial function, a function defined by a polynomial, and this is the solution set of a polynomial equation or an inequation or whatever more complex formula you have. Yeah. Okay. So just some comments that since m to the 0 is as cardinality 1, truth values can be treated as zero-array relations on a structure. In case a predicate language consists of zero-array relation symbols, then the notion of interpretation defined below will recover the notion of a valuation in propositional logic, what we have defined earlier. So in this way, we could have just started with first-order logic, and propositional logic would just be a part of it, but it is always a good idea to just look at some lower complexity fragment first to get feeling of what is really happening, and then we do this. Okay, so now I will pour a lot of definitions onto you, but I will not be very precise with them because I have already explained the ideas, and I invite all of you to go through these definitions by yourself in detail. So an L term is constructed inductively using following rules: that each free variable is a term, each constant symbol is a term, and you can apply iteratively a function symbol to terms. Yeah, so whatever variable occurs in one of these terms is known as a variable necessary for that term. And fourth one, as always, it is the most important clause. It says that that's all. The set of terms is denoted by TL, and there is unique readability theorem for TL as well. So just to give you some idea, if we talk about L set, so recall that L set did not have any function symbols or constant symbols. Then the terms corresponding to that is just the set of free variables, nothing else. You cannot obtain anything from TE2 or TE3. It is just TE1. And similarly for L odd, because there were no function symbols in L odd or constant symbols. Then here, when talking about TL ring, yeah, it is the set of polynomials. Yeah, TL ring is the set of polynomials with finitely many variables. And here I have written a question for you, like what are the coefficients of these polynomials?
The constant symbols.
Not just the constant symbols, something
Functions
more.
applied on the constant symbol.
Correct, correct. So if we are using 0 and 1 as constant symbols, then they will be integer coefficients. Plus, you have dot, you have minus. Okay, so TL ring is the set of polynomials. So we have a separate name in logic to talk about polynomials. They are just terms. Okay, so an L formula is once again constructed inductively using the following rules, that you have an M-array relation symbol and M terms. Then those L terms, then then R applied on those M terms is a formula, or equivalently equality applied on two terms, because equality is a binary relation symbol. This is also a formula. Right. And if F2 stands for what we did in propositional logic, that if phi and theta are formulas, then so are negation phi and theta, conjunction theta. And if phi is a formula which does not mention, this needs to be explained. If phi is a formula that which does not mention wj, a bound variable, then you can replace all occurrences of the free variable xi by the bound variable wj and put there exists wj in the beginning of that. Then phi wj replacing xi and all the other variables as it is a formula. Okay, so you simply replace a free variable by a bound variable and put a quantifier in the front, and that becomes your formula. And that's all. You can apply, of course, do this iteratively. Yeah, the set of all formulas is denoted by FL. Atomic formulas are those which only use F1 and F1 prime. Yeah, only relation symbol applied to terms. Quantifier free formulas which only use F1, F1 prime and F2 iteratively. And sentences are those which do not have any free variables. We already saw that. So let us look at some examples. Without that, it won't be clear what we mean exactly. So x1 equal to x2 is a formula. x2 equal to x3 is a formula. Then their conjunction is a formula. And this conjunction implies another formula is also a formula. So it is a quantifier free L set formula. I'm sorry about this. This is a typo. Sorry, righto. Yeah. Phi x1, x2, x3, not x, y, z. Then you look at this psi for all w1 for all w2, w1 star w2 is w2 star w1. This is an LGR sentence because it doesn't have any free variables. And how it is constructed? You first constructed this term x1 star x2, then you constructed x2 star x1, then x1 star x2 is equal to x2 star x1 is a formula. It is an atomic formula. Then you replaced the occurrence of the free variable x2 by w2 and put a quantifier. Then you replaced all occurrences of variable x1 by w1 and put a quantifier for all w1. And this is how we have constructed the formula iteratively using those rules. Yeah, this is how you construct terms and formulas. Right. And if you are given an L structure, the value of a term tx1, x2, xn at a particular tuple, you have to choose the same number of elements in this tuple as many variables occur in that term. Written, the interpretation of T in M at A bar is defined inductively as follows. If Tx bar is xi, then you simply choose the ith entry of this tuple AI. So for example, if your term is Txy, Txy is the notation for your term and it says x. then txy interpreted at 1, 2 is just 1. It picks out the first coefficient, first entry. Then if it is a constant symbol, then it doesn't matter what your a bar is. It is always going to be the interpretation of the constant symbol. Yes, there is something in the chat. Do we need to distinguish between a free and a bound occurrence of variable and a free bound variable in a formula? That's why I'm using different symbols so that there is no ambiguity. If Ranjan, if you want to say something else, you can unmute yourself and say that. Okay, fine. That's why I'm using different notation. W is my notation for a bound variable. And in my F3, I was clear that I'm replacing some xi by a wj and then putting a quantifier so that there is no ambiguity anywhere. I know I'm going really fast with this, but you have understood the model example of polynomials, polynomial equations. So that's why I'm going fast. So C is a constant symbol, then you just interpret it as its interpretation in the structure, original structure. Like if C is interpreted as 0, then no matter what a bar is, it will always be 0. PM a bar will be 0. And if you have a more complicated term, which is a function symbol applied to terms, then you simply apply the interpretation of that function, function symbol, which is a function which has those many arguments. Those arguments are calculated inductively. So T1, T2, Tm are terms with lower complexity. So by induction hypothesis, we have already computed the values. We have evaluated them at a bar, and therefore you can apply Fm on that M tuple of elements of M. So let us look at an example that if x1 star x2 star E is a term, then its value in N2 plus at 5, 6 is you simply replace x1 by 5, replace x2 by 6 and E by 2, and you add. This is just like sometimes you like if you are looking at it for the first time and you don't like abstraction as much, you will think that we are not eating like this, we are eating like this. We all of us understand what this means. Replace x2 by 6 but you cannot do it in a haphazard manner. You had to be carefully explain the algorithm of evaluating a term. Any questions so far? Okay. So now interpretation of polynomial equations or inequalities, which means interpretations of formulas. So let M be an L structure and theta be a formula. So we say, this is important, that theta x bar is satisfied in M by an n tuple in M, which is written as M models theta of a bar as follows. We have to give an inductive definition, and here appears the double turnstile symbol, which means theta is true in M at a bar. If your formula contains variables, free variables, then you cannot say theta is true in M alone. You always have to specify theta is true in M at a bar. Whereas if theta was a sentence, then you don't need to say that. Theta is true in M, that's all. Okay. So this is T1, truth 1. So if theta is of this form, relation symbol, then when do we say that this is true? If and only if the tuple T1 M a bar, these values we have already calculated, evaluated. So this tuple belongs to Rm. Yeah, so Rm was already a well-defined thing from the structure itself. So we'll say that this formula is true if this tuple belongs to Rm. And this Rm was our choice while defining the structure. Similarly, we say that this particular type of atomic formula is true at A bar if these two terms give the same value at A bar. T2 I have already explained. Yeah, this is just the syntactic negation and conjunction converted to semantic negation and conjunction. Yeah, this negation symbol is not, and this conjunction is and, English language and. Okay, the last is something which needs to be explained. Yeah, if theta of x bar is there exists Wj, phi x bar Wj. Yeah, so originally it was the formula phi x bar y for some free variable y, and we have replaced that free variable y by a bound variable Wj and put this quantifier. So this happens. So theta is true in M at A bar if and only if there is some B in M such that M models, so phi is true in M at A bar comma B. So once again, I want to emphasize on this that there exists symbol is interpreted as there exists over the universe. Yeah, the English language there exists over the universe of your structure. And then we put a B here. So phi actually is a lower complexity formula than theta. And then this definition we already have by induction. Okay, so just like negation, for the syntax for negation was interpreted as negation, syntax for conjunction was interpreted as English language and, this symbol for existential quantifier is interpreted as English language there exists. Yeah, that is why this is called semantics. We are talking about double turnstile symbol here. Okay, so that is why, like, once you know what this means, what is the English word for there exists symbol, you automatically know what it means. Like, you can read out formulas very easily, because that information there exists and or that information is fed in your brain already. You just use that information and process the data. But when we are trying to describe it as a mathematical discipline, we have to actually describe this carefully. Yeah, we have to explain what we mean so that our intuition actually agrees with what the formal thing has to say. Okay, there is one more question. Yes, universe is the syntactical. No, it is semantic counterpart of model. No, I will define a model, Agnivo. Wait for that. I have only defined the structure so far. Model is with respect to a set of axioms. Yeah, so we haven't done anything about that yet. Don't confuse the word structure with model. Okay, so let us look at couple of examples that if theta xy is rxy in L odd, then you can say that this relation R, like Rxy, is true in n less equal at 5,6, because phi is less equal 6. And if psi is the sentence in the language of groups which says that for all W1 there exists a W2 such that W1 star W2 is E, then R0 dot does not satisfy psi. Yeah, because this says that there exists an inverse. What we are saying, that there exists a right inverse for each element. But of course, with respect to multiplication, 0 doesn't have a right inverse. 1 doesn't have a right inverse, so we cannot say that. So psi is not true in R0 dot. Okay, anything to say so far? Any questions? I'm just abstracting out the notions that you already know. Yes, Dhruv?
Sir, the formula is saying that we want W star W1 star W2 is equal to 0, right?
Is equal to E, yes.
E is 0 in this
Yes,
structure.
interpreted as 0, yes.
But then W2 equal to 0 we can always take for any W1.
Oh, sorry. I missed that. I should have said R1 dot.
R1
Sorry
dot.
about that. Yeah. With that intention, I wrote this. Thanks for the correction. Yeah. Any other things to say? Okay, so in that case, I want to take a diversion from my notes because SMS wants to talk about Gödel numbering and axiomatization. So I will just follow his book for some time. Yeah. So this is what I have opened. This is his book on a course on mathematical logic. And he talks about a proof system in his book. I'm not going to prove completeness. And if I don't need to talk about completeness, I don't need to talk about proof systems. But because he needs it, we are going to describe them briefly, these things briefly. Yeah. So let L be a first order language. His notation is a bit different than our notation. But the propositional axioms he will take as logical axioms. He is describing a proof system here. Propositional axioms are the formulas of this type. Yeah, negation A or A is a tautology. So he is assuming them as logical axiom. Then identity axioms, that X equal to X, where X is a fixed variable, those are identity axioms. Then equality axioms, I suppose here there are parentheses. Yeah, Y1 equal to Z1 implies Y2 equal to Z2 implies Yn is equal to Zn. Then when all of, or you wanted to say conjunction here.
No. Yeah, you can put it that way also.
Yeah. If Y1 is equal, so if all Yi's are equal to Zi's, then and F is an n-ary function symbol, then actually F of Y1, Y2, Yn is equal to F of Z1, Z2, Zn. I mean, this is just saying that equality should behave in the way that we expect it to behave. And similarly, yeah, so here we had equality, but if P is a proposition, so if P is a predicate, then we will say that if all the Yi's are equal to Zi's, then a predicate is true at Yi's if and only if that predicate is true at Zi's. I'm just replacing it with if and only if, doesn't matter. Yeah, you can always swap these things because of we have symmetry of equality.
But this is what the axiom is.
Yes. Yeah. So
you can deduce from there. But
yeah, you can deduce from that. Axiom is that P, the predicate P is true at Y bar, then predicate P is true at Z bar. Then you can substitute. Okay, so the formulas. So if a formula A with x1, x2, xn is true at some
no, there is single variable here.
That is single variable. I don't know what your notations are.
No, this is that if A is true for x equal to t,
yeah,
then there exists xa is true.
Okay. So if you already have a witness, then you can say that there exists a witness.
Yeah, there exists xa is true.
Yes, there exists an x such that A is true. And the rules of inference. So last time we had modus ponens. So here there are more. So this is the expansion rule, that if you have A, then you can infer B disjunction A. Yeah, this is something bigger in the sense of implication. So you can infer that. Then contraction rule, if you have A disjunction A, then you can infer A. From that, this is quite obvious and also intuitive because these two formulas are logically equivalent. And associative rule, that if you have this, then you can infer this. Again, very intuitive. Cut rule. Yeah, this is I think similar to some version of modus ponens, that if you have A disjunction B and negation A or C, then you can infer B or C. And finally, there exists introduction rule that if X is not free in the formula B, then actually it doesn't matter. Yeah, you can A implies B. From A implies B, you can say there exists XA, like there is a parenthesis here, there exists XA, that will also imply B. And I think the main thing that he will use is that this is if your language happens to be countable, then this is a countable list of logical axioms as well as countable list of rules of inference. So that is what you will use. Yeah. Do you want to say anything?
Who, me?
Yeah.
No. Continue
Okay.
with the definition of proof. That's all.
Yes. A proof is again proof in T, a theorem in T, etc. are defined as before. So proof is a finite sequence of sequence, yeah, as before. A finite sequence of formulas of your language, such that each formula can be derived, is either a logical or non-logical axiom of T, or it can be inferred from the previous formulas by a rule of inference. Okay, so just like we did last time, like modus ponens can be applied on two previous formulas. So similarly, same thing here, but it's just that we have access to more rules of inference over here. So this is a proof, but again, the important thing is that a proof is a finite sequence of formulas. Yeah, that finiteness will be exploited heavily in the next lecture. Okay, so any questions about this?
Just give the definition of a theorem.
What is a
This is a proof of AN.
Okay, A is a theorem of T if there is a proof of A from T. Yeah, if A can be deduced from T. Yes, somebody is saying something, I think. No. Yeah, in my lectures, I'm not going to refer to this again because I will only do a proof of compactness and not completeness. So I don't need a proof system. But if you have any questions about this, just ask. Okay, so in that case, I will go back to what I was saying, and I will just cover one more definition and then I will stop because it's almost time. So let L be a language and gamma be a set of formulas. But what we require is that we are only using finitely many free variables. So gamma could be an infinite set of formulas, but the free variables appearing in any formulas in gamma are amongst x1, x2, xn. And theta is any other formula. Then we say that theta is a logical consequence of gamma, which is written like this, that the gamma double turnstile theta, if for any L structure M and any assignment A bar to X bar with A bar in M, like whenever phi is true in M at A bar for all phi in lambda, then theta is true in M at A bar. So very similar to last time, but please pay attention to this, that earlier we said for all valuations, whenever left-hand side is true, then right-hand side is true. Now here we have to say something more. Whenever, so valuation is replaced by a structure. So for all L structures M and all assignments A bar to X bar with A bar in that respective structure, whenever left-hand side is true, which means for all fine gamma, phi is true in M at A bar, then theta is true in M at A bar. Okay, so definitely pay attention to this, because this is a source of confusion for if you are learning it for the first time, that there are two for all things. So for all L structures M, then there is a dependent for all, and for all assignments A bar to X bar in M, yeah, with A bars in M.
Sir, why are you using finitely many x1, x2, xn? Gamma is finite.
Gamma could be an infinite set of formulas, but we are just putting a restriction that they together they cannot contain infinitely many variables. We want some finiteness assumption.
Okay.
So the only free variables which are used in any formula of gamma are amongst x1, x2, xn.
Okay. So there is some bound on the n-ary thing.
Yes. Otherwise, we can't conclude this. See, the main point being that the right-hand side is always going to be a single formula.
Yes.
Which will use only finitely many variables.
Yes.
So let us not worry about the remaining variables. So in that sense, we're taking this restriction.
Okay.
We are anyway interested in learning whether theta is a logical consequence of gamma. Okay, so for example, you can see that if for all W1 there exists W2 such that RW1 W2, this models, this has a logical consequence that there exists a W1 and there exists a W2 such that RW1 W2 holds. This side says that R is a non-empty relation. Yeah, there exists W1, there exists W2, RW1 W2 means it is a non-empty relation, whereas this one says that for all W1 there exists, for all first components there exists a second component such that something is in relation. So therefore from here you can conclude this. But the important thing to observe is that this doesn't depend, like this relation, this double turnstile relation does not depend on which structure you are working in. For any L odd structure, this will always be true. Okay. And next is the definition of model, and I will start with that tomorrow. So any questions for this? I know I have gone really fast, but you know the ideas and you can sort of connect them with propositional logic and as well as with the polynomial example. That's why I went fast. Any questions? No?
Sir?
Yeah?
So, sir, if we take a structure where the thing which the binary relation which corresponds to the symbol R is empty. So then this formula for all W1 there exists W2, so that R W1 comma W2. Is this not satisfied in that structure?
No. So in that structure, if your interpretation of R is empty, then this formula itself is not satisfied. So see, here there is a whenever this holds, whenever phi holds true in M, then theta holds true for all phi in gamma, then theta holds true in M. So if this side is itself false, then you shouldn't worry about the right hand side.
Yes.
Yeah, I mean the left hand side formula is itself not true. In that case, you don't worry about right hand side. Whenever the left hand side formula is true in a structure, then you worry about whether the right hand side formula is true or not.
Sir, but isn't it vacuously true that for all W1 there exists W2 such that RW1 W2?
No. See, your universe always contains at least one element.
Okay, yes.
Yes, that was our assumption to begin with. Universe is a non-empty set. Yeah, so good question. So universe is a non-empty set. So for at least that element, there should exist some W2, which is not true if your interpretation of R is empty. And therefore, yeah, there is no question about checking the right-hand side.
Yes.
Yeah, any other question?
Can I ask a question regarding something like which was discussed at the beginning of this class, like not this particular section?
Sure.
So this was about when you mentioned that like the proof that we gave. I mean, in our in the proof for completeness, we made a construction of a maximally consistent set.
Yes. Yes.
And you said that the proof will not be like the proof is not constructive in that case.
Yeah.
So I'm not sure why we would expect a constructive proof in that case, because the hypothesis, the objects that we're using in the hypothesis of the construction, those themselves are abstract. Like there are no distinguishing features for those objects that you're taking. So like, if there would have been a construction, then there is nothing to use to construct anything in such a proof.
But
so why would we...
so the point is that even if you know something more about the S that you are starting with, yeah, a consistent set that you are starting with, still you don't have any control over what maximal extension you get, maximal consistent extension.
Okay, sir.
Yeah, and you don't have any control over what exactly is that maximal consistent extension. That is what we mean by non-constructive.
Okay, sir.
Should I go ahead?
Yeah. Yes, okay.
Okay, thank you for the talk, sir. I think we'll take a break of 1 hour for the lunch, and let's meet at 2:15, which is the time for the next talk.
And please ensure you have at least had a look at the tutorial sheet available on the website. And yeah, one more announcement, like there are fewer people, that if you need, you are of course supposed to come up with your own topics for student presentations, but if you need to discuss something, then I will be available after the tutorial session. Yeah, about presentations.
Sir.
Yeah.
So is there a possibility that if you are not able to get a consensus on a partner or a topic, can we do it alone with a shorter time? The presentation, the student presentation I'm talking about.
I mean, if you want to attend that meeting, we'll discuss more about that. I think we should give more chance to groups so that more people are involved. If there is very low participation, then we can allow individuals to present.
Okay. No, in case it is individual, we can do it with less time and
Oh, yeah. But yeah, isn't the point of attending a school is to network as well?
No. I'm talking about if the topic is not reached by consensus and people are not ready to work on some things. That
I mean, let us see. I don't want. Yes, Sujata.
Can I please say something?
Yes, please.
Yeah, Pratik. So, can you please wait, as Amit said, that we will discuss about it more after his tutorial. So, can you please wait till then? Then we can discuss about all these issues.
Yeah, sorry, ma'am. It was just a general question.
No, yeah. No, we welcome such questions.
Yeah,
please,
definitely.
I'm really thankful that you asked this question. So, I'm just saying that please be there. We will discuss about it.
Sure, ma'am. Sure.
Okay, thank you.
Prasenjit, empty function could have any codomain, but the range is empty. Yeah, let us stop for now. Yeah,
so there is no function from empty set to empty set.
There is one function. That is the identity of that empty function, empty set.
So what is the 0 to the power 0? We say that.
It is 1.
Oh.
To be consistent with cardinal arithmetic, it is 1.
Okay.
Yeah. Okay. Yeah, SMS, you want to say something?
No. I heard
Okay.
something cardinal arithmetic. I don't know. Consistent.
0 to, so what is the identity function on empty set? Like that was the question essentially. Is there a function from empty set to empty set?
No. You see, you made a somewhat mistake. You see, GUI function. That I would not have even talked of. Now would have talked of GUI relation. I would say that the constant functions, the constant symbols, and arity is always greater than equal to 1. What happens is that sometimes we say that GUI functions are treated as constant. So this only raises a lot of questions, and I find it totally unnecessary. Let's say we have constant symbols, and arity is greater than equal to 1. You don't look at GUI relation symbol.
Those are propositions.
GUI relation symbol on a set. Yeah. Arity of either it is a unary relation or a binary relation or a ternary relation or a ternary relation. Okay? In mathematics, that is what happens.
Okay.
So my strategy is, for me, arity is greater than equal to 1.
Okay.
Constant symbol. This is much less confusing. Okay? All these are mathematicians, mathematics students. Empty function is again, like madam has carefully avoided empty function. She could have said that empty cross half 0, 1, there is a bijection to empty set. And therefore that first thing is non-empty. Okay? But then she said, oh, this empty function will confuse. So she already gave the example of n cross 0, 1 to n, there is a bijection. And if x is infinite, there is n inside. Therefore, that partially ordered set is non-empty. N cross n to n, there is a bijection. Therefore, when you are proving that x cross x and x, there is a bijection. Even empty, if you take, for that she defines a partially ordered set consisting of all AF such that F is a bijection from A cross A to A. So why is this partially ordered set non-empty? Now you can take A to be empty set. Okay? But then a function from empty set to empty set, 70% of these students will say, oh, these guys are mad, let us not listen to them. That is how mathematics and psychology work. Because they have never seen function from empty set to empty set. Okay? So I deliberately, and she also did herself, avoid these things. Okay?
Okay.
So why is now you explain to the student why is the GUI function a constant? You have increased your work, and one always tries to decrease one's work. Then your life will be simple. You play those cards carefully. Okay. I have to eat and come back for my lecture. Okay.
Sure.
So I am leaving.
Yeah.
Yeah, let's meet at 2:15.
Yeah, you can.
Yeah. Thank you so much, sir.
Bye.